Dr.
The reporter Madhusudan is available.
Report.
Yes, sir. Yes, sir. I'm here, sir. Should I start, sir?
So you can just start it.
Yes, sir. Good morning, sir. This is Vivek Asana.
Reporters is here.
Everybody, welcome to all. So our reporter, Mr. Madhusudan from IIT Kanpur, as he joined.
Madhusudan, are you hearing me?
Yes, sir. Yes, sir. Shall I
Yeah,
start?
so please start from your side and you read the citation of Dr. P.V. Venkatakrishnan, who is the Honorable Chairman of this session.
Okay, sir. Okay, sir.
Okay, please.
Okay. Thank you. Thank you, sir. Good morning, everyone. I'm Madhusudanan from the Department of Aerospace Engineering, IIT Kanpur. This is technical session 3, structures. So it's my privilege to introduce our session chair, Dr. P.V. Venkatakrishnan, to everyone. Currently, he is the director of ISRO Propulsion Complex, Mahendragiri. He started his career.
No, there is something wrong. Actually, you are reading something old one. I am retired now, and I had sent to.
Okay. He did it.
I'm really sorry, sir. I got only.
No. I had sent to Sen already once. I don't know whether what. I can tell about myself. I was an IPRC director, and after that I was associate director Vikram Sarabhai Space Center, and I took as the first ever director of a capacity building program office, which was started newly as a fourth vertical of ISRO for infrastructure generation, industry cooperation, indigenization, everything put together. It's a big initiative. And I was the founder director for that for 3 years, and I was superannuated last year and continuing in ISRO headquarters right now as Professor Sadish Dhawan, scientist and distinguished scientist. Okay, thank you so much.
Thank you, sir.
Madhusudan, I think
Krishnan
already told.
No, it should be correct. No, whatever we tell should be correct. No, should not.
Madhusudan will correct. Madhusudan will correct.
Now we can continue the session.
Whatever he
now we can continue the session, Madhusudan. Yeah.
Yes.
Okay, sir. Thank you, sir. I'm sorry for the inconvenience.
Please go ahead.
Okay, sir. Now we'll go for the paper presentation. The first presentation is the topic, effect of slot geometry on the thermostructural response of deployable composite booms. They're presented by Karishma Parthiban, and the research group is Vinu M. Kudayakos and Dr. Srihari VM. The presenter is Ms. Karishma Parthiban. I think she is here.
This is from Shastra University, no? Am I right?
Yeah, sir. They're from Shastra Deemed University, Tanjavur. So, Ms. Karishma, you have 10 minutes of presentation and followed by 2 minutes of question and answer session.
Can go to that presentation mode. Now, okay, fine.
Yeah. Okay, sir. Good morning to one of all present here. I'm Karishma Parthiban, currently pursuing a bachelor's in mechanical engineering at Shastra University, Tanjavur. On behalf of my co-authors, Vinu M. Kuriakos and Dr. Srihari VM, I would like to present my student project work on the effect of slot geometry on the thermostructural response of deployable composite booms. I would like to express my sincere thanks to Institution of Engineers, India, for giving me the opportunity to present my work in the 34th National Convention of Aerospace Engineering. I would also like to extend my thanks. Yeah. Sorry.
Hello.
Yes.
You can. Others can mute the mic, please. That is disturbing. Actually, if somebody else is speaking, others can mute the mic, and you can continue.
Okay.
Yeah.
Hello.
Continue, yeah.
Hello.
You please continue.
Hello. Others can, other than the author who is speaking, can all others, can you mute the mic, please?
Hello.
I would also like to extend my thanks to my project supervisor, Dr. Srihari VM, Associate Professor in Aerospace Engineering, Shastra. This is the outline of my presentation. Every man-made structure that is there in this space, such as the artificial satellites, space telescopes, and even the International Space Station, requires at least one large antenna in order to maintain a robust communication link. But the limitations on the payload, geometry, and dimensions there is a difficulty in launching the large booms. However, this constraint can be overcome by the use of deployable structures that have the ability to be folded, carried, and deployed whenever needed. There are different classes of deployable structures, including in-orbit assembly structures, structures that have mechanical hinge joints as well as sliding joints, and high-strain structures. This work is mainly related to the high-strain structures, usually constructed with high-strain composite materials. The motivation for this work of including composite materials in space linkages is because the booms made of composite materials are ultra lightweight and have superior stiffness and strength. They also increase the packing efficiency with a light weight, making the missions more economical. The results from this work will be highly significant and relevant to the space activities and will be useful for employing ultra lightweight composite booms in several aircraft mechanisms. There are many numerous studies in the field of deployable composite booms. For the sake of brevity, I would like to highlight a few studies that are relevant even to my study. So E and Pellegrino in 2005 studied the deformation and strains induced by folding of carbon fiber reinforced composite hinge tubes. It was observed that the larger the folding angle, the firmer the tube hinge snaps to a straight configuration. However, we know that the smaller the folding angle, the lesser will be the strains generated. Malekirci and Pellegrino in 2009 studied the deployment dynamics of composite materials with an integral hinge. It was observed that the stress concentrations were high at the hinge region. Xiang et al. In 2019 performed the folding analysis of deployable composite booms with a lenticular cross-section. It was observed that the main failure mode in these lenticular booms was due to buckling. The objective of my work is to design and perform thermostructural analysis on deployable composite booms with various enclosure geometry. In this study, we have limited our enclosure geometry to a circle, ellipse, and parabola. Initially, we have performed few validation studies in order to compare our experimental results as well as the numerical results. We have actually manufactured a deployable composite boom with a slotted hinge and with the glass fiber epoxy composite. The material properties were tested at PSG Coimbatore. In the software work, the boom was given cantilever boundary conditions and a concentrated tip load at the end. Both the displacement values at both the ends of the slots were determined, which is actually at 75 mm and 155 mm from the root of the boom. It was observed that the deflections produced in the simulation as well as experimental results were more or less comparable. The design for the current work is that we have designed 3 booms that have dimensions identical, but only the slot geometry is changing. So here, this is a boom having slot with a circular enclosure. The second one has an elliptical enclosure, and the third one has a parabolic enclosure. The coordinate system that is given here can be used to refer to the longitudinal axis, transverse axis, as well as the radial axis. Once the design of the composite boom was made, it was assigned with the metal properties of unidirectional epoxy carbon. Two layers of composite fibers, each of thickness 1 mm, oriented in 45° and minus 45° was used to create the boom. So during the boundary, as the boundary conditions are, one end is fixed and there is a so one end of the boom is fixed and there is a tip load applied at one end. This tip load was applied in all the three directions in order to account for the various loads the boom may be subjected to during and after deployment in space. So from the test, we understood that the significant results were found only when the boom was loaded along the direction, when the deflections were along the direction of loading. So these maximum deformation values were tabulated and are presented here. In this graph, we can see that the boom with the elliptical slot geometry have a higher deformation rate than that with the parabola as well as circular enclosure. The boom with the parabolic enclosure has least deformation in compared to the other two. The deformation along the z-axis was of the magnitude 10 to the power minus 3. So this is plotted in a different graph. Even in this test, it was observed that the boom with an elliptical enclosure has maximum deformation. The boom with circular as well as parabolic enclosure has almost similar deformations. The next test was done to estimate the maximum stresses developed in the boom when loaded in different directions. This graph represents the load versus maximum stress. Here we can clearly observe that the boom with a circular enclosure undergoes maximum stress, whereas the boom with a parabolic enclosure has the least stress. Given that the boom can be exposed to various temperatures, an investigation was carried out with a temperature variation of 73 Kelvin to 973 Kelvin. As epoxy degrades at further higher temperatures, cases exceeding 700 degrees Celsius were not explored. The deformations and the stress values were measured with a constant tip load of 600 grams and varying the temperature. The thermal coefficients are given here. This is the graph of the temperature versus maximum deformation for all the three booms. Here we can clearly witness that the deformation is minimum when the boom is exposed to a temperature near to the control room temperature, which is around 273 Kelvin. As the deflection of the temperature, deviation from the room temperature increases, the deflection also increases. Even under thermal environment, the deflections in the elliptical boom with an elliptical enclosure geometry has maximum deformation. But here, the boom with a circular enclosure geometry has lesser deformations as compared to the previous study under control room temperatures. The maximum stresses along various axes of loadings were quantified and are tabulated here with the varying temperatures. From this table, we can understand that the parabola, the boom with the parabolic enclosure, still performs better than that of the booms with the elliptical as well as circular enclosure. From this, we can conclude that the boom with a parabolic enclosure has highest loading capacities. I would like to conclude by giving a brief summary of the study. It was observed from the literature survey that a detailed study on the effect of slot geometry on deployable composite booms is desired because of the fact that stress variations occur near the slotted hinges. The initial design was modeled in ANSYS software, and a similar space structure was manufactured to validate the results. It was found that the deflection values obtained from the computational as well as the experimental analysis were comparable. Further thermostructural analysis was performed by varying the enclosure geometries. Here we have limited the enclosure geometry to a circle, ellipse, and a parabola. It can be observed from the study that the boom with a parabolic enclosure shows a better overall performance under controlled room temperature as well as various thermal environments. The deployable composite boom with slotted hinges of 2 layers are having a stress strain generated values of lower magnitude, which proves the relevance of the present design. Thus, it's important to quantify the effect of slot geometry in deployable composite booms with slotted hinges, and several parametric study results are presented to highlight the significance of present design in space application. We would also like to extend our study to a lenticular boom, a deployable composite boom with a lenticular cross section. These are the references that were used for the studies. Thank you.
Thank you so much, Ms. Karishma. And now this is a very nice presentation. So this is for a question and answer session. So any questions?
My only question is, why did you limit to these 3 geometries alone? Is it the one which is already prevalent, or okay, you want a smooth this one transition? There should be sharp corners or rectangles and squares and all kind of things. Okay? Because
yes,
then among the smooth ones, why did you select these 3 alone, ellipse, circle, and parabola alone?
Sir, as if we define 2 slots with sharp edges, there can be stress concentrations, sir. So which will lead to the failure of the boom prior than the actual what is desired.
And what actually deployable booms are in the space already. Once it is reaching the space, you are deploying it. Am I right?
Yes, sir.
Then the radiation is the thermal effect is the radiation what is coming. Am I right?
Yes, sir. Yes, sir.
So the radiation will not be uniform actually. The radiation will be different on different times and different angles depending upon the sun, everything and all. So
yes, sir.
the study was limited to what temperature you have been varying the temperature from 73 degree to 973, and what is the increments you are given for temperature each one? Anything?
100 degrees. 100 degrees Celsius, sir.
So how many 73 to 973 is around 8 studies. Am I right?
Yes, sir.
Any effect of any temperature load combination? Did you notice anything more anything, or was it linear or anything any abnormality you noticed? Because the geometry will not be uniform actually. Deployable antenna geometry also, the hinges and all, no, it is not a totally uniform structure.
Yes, sir.
So what will be the effect of the combination? Anything which was specific to some temperature load combination? Anything was more or less? Anything did you infer from the studies? What did you conduct?
Sir, we have only considered the maximum loads, maximum stress values.
Maximum temperature, maximum load.
No, sir. Maximum stresses that will be in the boom.
At what temperature load combination was having the maximum stress?
Sir, as the temperature increases, the stress value is going to increase, sir. There'll be more thermal stresses induced in the.
So whatever you shown was linear. Am I right?
No, sir. The actual
the graphs, whatever is shown was almost linear. Am I right?
Yes, sir. Yes, sir.
It reduces and increases.
Yes, sir.
then you are concluding parabola is the right one.
A parabola seems to perform better than the other two geometries, sir.
Okay. Why lenticular? Next study. What is the peculiarity of that particular cross section?
Sir, this can be folded and rolled up, sir. So it will consume more less space than that of the booms with.
Okay,
so
it's a study actually. Okay.
I would like to comment one thing. The parabolic shape seems to be better, definitely, but there should be some ratio of the minor axis and major axis which will play a role, and the remaining wall thickness. These parameters will be also relevant. Now you have studied a particular case of wall thickness. Am I correct?
Yes,
Hello.
sir. Yes, sir.
After the cutting of the particular shape, there is a remaining thickness in the shell. That is one parameter which decides the stress. Then the cross section parabola is of course better because it is better cantilever, if you say that way. But the shape of the length, major axis and minor axis, the ratio also may decide the stress levels.
Yeah.
So my question is,
studies.
Yeah, my doubt is why did we study the particular size of the hole or other cutout? What was the significance?
Sir, actually, we did not restrict to different lengths of the major and minor axis, sir. But probably we would further study that as well.
What Ashok, what I think, this was a very a project study from the student. That is actually she has concluded now parabola is a better shape now.
That is very much agreeable.
Within parabola, she will have to optimize now. That's the next step.
Okay, fine. It's a good study anyway, no doubt.
Any other questions? If there are no further questions, I think we can conclude. If any other questions are there, we will give one more chance for audience or anybody to ask any questions.
Any other questions?
Okay, thank you, Karishma. Then, so then you can move to next paper.
Yes, sir. Thank you, sir.
Thank you, sir.
Thank you.
Thank you. So the next presentation is implementation of fault tolerance control in distributed system during structural testing of launch vehicle subsystems. The authors are Mr. Chippy V and Ms. S. Sweet Annie Grace, Mr. G. Kamlesh Davidson, and Mr. J. Murugananda Bhaskaran. I think the presenter is Mr. Chippy V. Am I right? Are you here? Yeah. Yeah, you can start the presentation.
Okay, sir. Good morning, everyone. Is my presentation visible, sir?
It is visible. Please go ahead.
Yes.
Okay, sir. Okay. Good morning once again. I am Chippy, and I'll be presenting on the topic implementation of a fault-tolerant safety interlock conditions in distributed system during structural testing of launch vehicle subsystems. So these are all the technical papers which have used for my reference study. So first I'll give an introduction with respect to the structural qualification test. Structural qualification test is mainly done to ensure the structural integrity of the flight hardware, as well as to demonstrate the capability of the hardware to withstand the different load conditions which the hardware will be subjected during different flight regimes. Usually will be subjecting the loads higher than that experienced during the flight, and the hardware and the performance of the hardware will be compared with the previously accepted or rejected criteria based on mission requirements, and thus the hardware will be either qualified or rejected. So in order to carry out the structural testing, this performance of the hardware needs to be monitored. Like different parameters of the hardware needs to be acquired, monitored, as well as analyzed, for which instrumentation system will be required. This instrumentation system we are categorized into two types. That is PLC based facility command and control system, and the second one is test statistical data acquisition system. Now PLC based facility command and and control system is nothing but a programmable logic controller, which will be used mainly for acquiring the process parameters as well as for controlling different valves in the fluid circuit. During structural test facility, during structural testing, the hardware will be pressurized using a gaseous nitrogen, as well as it will be filled with a liquid nitrogen to simulate the cryogenic conditions. For which we will be using one fluid circuit. So this fluid circuit will be comprising of different pressure transmitters as well as different electro-pneumatic valves and control valves. So for acquiring the pressure parameters from the fluid circuit as well as for controlling the different valves in the fluid circuit, this PLC based control system will be used. We are using a single standalone PLC system with a cycle time of 100 milliseconds. Now, coming to the test article data acquisition system, the hardware which will be subjected to the structural testing is known as test article. Like it can be any hardware, like different flight tanks or some different hardwares will be subjecting to structural testing. So the performance of the hardware we are assessing based on the some parameters from the hardware, like strain, temperature, displacement, etc. So all those parameters will be acquiring using a separate test article data acquisition system. It is we are having an integrated signal conditioning and data acquisition system with a total channel capacity of 2248 channels, and the sampling rate of the system, it is software selectable. We can select from 10 hertz to 5 kilohertz. Now, as I told earlier, there is a fluid circuit for pressurizing the tanks as well as for filling the tanks with LN2. So this fluid circuit mainly comprises of a tank filling circuit, pressurizing circuit, vent circuit, and command circuit. And moreover, it consists of EP, electro-pneumatic valves, manual valves, pressure gauges, and pressure transmitters. So this pressure transmitter senses the hardware tank pressure, and two electro-pneumatic valves in a normally closed configuration, which will be connected in series at the pressurization end, and the two electro-pneumatic valves in normally open configuration connected in parallel at the vent side. So based on the tank pressure, whenever the tank pressure is crossing the desired level, the two EP valves at the pressurization end will be closed, and the two EP valves in the vent side will be opened to bring back the hardware to safer condition. Now, this is the safety interlock logic. Safety interlock logic is basically used for ensuring the flight hardware safety during a structural testing. It takes care of the chances of exceeding the pressure values experienced by any hardware. Usually, the interlocks will be enabled at 1.03 times the ultimate pressure value for each hardware. For example, the hardware is a propellant tank, and as per the mission requirements, the ultimate pressure of the tank will be mentioned. For example, 9 bar. So if the ultimate pressure is 9 bar, we will be setting the interlock conditions at 1.03 times the 9 bar. That is 9.27 bar. That is, interlock conditions will be set whenever the pressure of the particular hardware exceeds 9.27 bar. The table shown here shows a sample interlock logic. That is, the first channel represents the pressure parameters experienced by the hardware. PT4 and PT5 are the pressure values experienced by the hardware. Then the corresponding low limit and high limit are being mentioned. That is, low limit is 0.7 bar and high limit we are mentioning at 9.27 bar. So whenever the pressure parameter of the tank exceeds this low or high limit, then the corresponding safety action will be taken. That is, action is closing EPV 1 and 2. As I mentioned earlier, two EP valves at the pressurization end will be closed in case if the limit value exceeds. That is, EP1 and EPV2 are at the pressurization end. So those two valves will be closed down, and the two valves at the vent side, which are EPV3 and 4, will be opened. Now, this interlock conditions we are executing using a SCADA-based mimic in the PLC. This is a sample SCADA-based mimic which we are using. So this using this GN2 cylinder will be pressurizing the propellant tank or hardware. So EPV 1 and 2, as shown in the figure, these two valves are at the pressurization end, and EPV 3 and 4 are at the vent side, and PT4 and PT5 are the two pressure transmitters which are used for sensing the pressure of the propellant tank or hardware. So this SCADA-based mimic will be used for monitoring the process parameters, that is this pressure parameters, and for controlling this electro-pneumatic valves. And all the safety interlock conditions will be set in the SCADA, and based on this pressure parameters, it will decide the closing or opening of this electro-pneumatic valves. Now the question arises, so all this interlock conditions we are setting in the PLC based SCADA system. So now the question arises, what happens if the PLC fails? We are using a single standalone PLC which can't tolerate any failure. So if the PLC fails means like upon exceeding the limit value, so there will be a catastrophic failure. So in order to withstand, in order to increase the tolerance of the system, we are proposing a methodology by using a test-statical data acquisition system for executing the interlock. So this is the proposed methodology. Now, as is shown on this PLC in normal acquisition mode will be monitoring the health status of the PLC. If the PLC is working perfect means it will execute the normal control operations and interlock execution. If the PLC fails, then one logic we are designing for detecting the PLC failure. And upon detecting the PLC failure, the test-statical data acquisition system will be intimated about the PLC failure, and this data acquisition system will execute the interlock safety interlocks to bring the hardware back to its safer position. Now, this is a detection logic of the PLC. So the PLC will be having a digital and analog input-output modules. So two digital outputs, which are mentioned as DO1 and DO2, we are taking from the PLC, and two DP/DT relays, R1 and R2, as mentioned, are connected in series. So whenever the PLC fails, DO bits will be 0. Through normally closed contacts, this failure of the PLC will be detected, and one buzzer and one LED lamp we are connecting, which will indicate the PLC failure, and through an auto interlock enable switch S1, this PLC failure detection bit will be passed to the data acquisition system digital input card. So apart from this auto switch, manual initiation for enabling the interlock can also be provided, which is provided using a manual switch S2, which will also be passed to the data acquisition system digital input card. Now, this is the interlock execution sequence. So as I mentioned earlier, this pressure transmitters in the hardware will sense the pressure, and this pressure value will be taken to a transformer isolator barrier. So this transformer isolator barrier is with dual output. So one output will be giving to the analog input card of the PLC, and one input will be giving to the analog input card of the test-statical data acquisition system. If the PLC is working fine, and the PLC upon reaching the limit values, it will execute the interlock logic, and the electro-pneumatic valves will be operated through the digital output card. So if the PLC fails, then the PLC failure detection digital output will be enabled, and it will be passed to the digital input card of the test-statical data acquisition system. So now in test-statical data acquisition system, corresponding digital output bit will be enabled based on the analog input value from the pressure transmitter, as well as the digital input value from the PLC, indicating the PLC detection failure detection. So using the corresponding digital output bit, the electro-pneumatic valve will be acted based on the interlock conditions. Now, this is the result while executing the interlocks using a statistical data acquisition system. So first graph indicates when the pressure parameter is coming below the 0.7 bar. This is with respect to the interlock table, which I have shown in my previous slide. That low limit was 0.7 bar and higher limit was 9.27 bar. So the first graph shows when it is coming less than 0.7 bar. So now the pressure value has become 0.699 bar. So during that time, the interlock logic got enabled in the statistical data acquisition system, and the corresponding digital output becomes 1. So now the time difference between this crossing of the limit value and enabling of the interlock we have estimated, and it is found to be 20 milliseconds. Similarly, in the second graph, the limit value, higher limit we have taken 9.27. So when it crosses 9.27, that is 9.271 bar, the corresponding digital output got enabled, and the delay we have observed as same as 20 milliseconds. Now, so this interlock conditions, which we have simulated in the data acquisition system with a sampling rate of 100 Hertz, the maximum delay it is observed to be 20 milliseconds. However, in our PLC with a cycle time of 100 milliseconds, the maximum delay for interlock execution we have found it to be 400 milliseconds. However, in PLC, whenever the pressure parameter exceeds the limit value, it will check the consistency of that pressure parameter for minimum 3 cycle times. That is 3 cycle times means 300 milliseconds. It will wait so that the particular pressure parameter is exceeding the higher or lower limit. Then only the interlock will be executed. So thus the maximum delay for interlock execution we have observed in PLC to be 400 milliseconds. So it can be concluded by stating that this statistical data acquisition system its sampling rate is higher, and with it has a higher time synchronization accuracy, because of which it has a lower reaction time in a interlock execution. And moreover, the PLC, since it is a single standalone system, it is a fault intolerant system. So by adding a statistical data acquisition system for redundancy in interlock execution, the fault tolerance it is increased. That is, the number of tolerable faults is increased from 0 to 1. So this ensures more reliability and availability of the system. So this is all about my presentation. Thank you, sir.
Thank you, Ms. Chippy. It's a nice presentation. So now the session is open for question and answers. Any questions?
Hello, Chippy, I have one question.
Sir, please.
You said PLC will be handing over to the data acquisition system in case of failure.
Yes,
I believe there is an internal mechanism to detect whether the PLC is failed or not. Okay. Now, is there any situation where the PLC gets activated further once a failure is detected? How do you ensure that the PLC is once for all removed from the system, or in case PLC is getting inadvertently added back to the control, how the system behaves?
Sir, actually, that's why we are taking 2 digital outputs in series to the data acquisition system. Like suppose if the PLC is not failing and some malfunctioning of the PLC is happening, because of which suppose one digital output it is getting either switched off or on. So if you are relying on a single digital output, it may be misleading. Like sometimes it may not be the PLC failure. That's why we have taken 2 digital outputs, and we can take either some 4 digital outputs connected in parallel series circuit to detect the PLC failure logic.
So now whether PLC comes back to life once it is declared as failed or not?
No, sir, there is no chance for that, because this is, if redundancy is there, means one more parallel system will be there which will take care of the failure chance. But it is a single standalone system, so if it is failing means it will completely go out.
Okay, then this next one more question I had was that the 1.03 times the pressure of the system.
Yes,
so on that I have 2 parts. One is, what is the sanctity of 1.03 times, because how close it is to the acceptable limit for the test article, number one. Second thing, with what accuracy it is measured and what accuracy it is acquired, so that the system will not be overpressurized. How that is ensured by numbers?
Sir, actually 1.03 times, it is based on each hardware mission requirements. Like for each hardware, it will be like some 1.03 times or 1.05 times we will be taking up. So that will vary based on a hardware. And for each hardware, the ultimate pressure will be mentioned in the mission requirements. Like as I told, 9 bar it will be mentioned. So like for a particular test case,
that I understood. Yesterday there was a presentation. My question was slightly different. How are you ensuring that you are not going close to that value by the time the system is failing and detected and switched over to the other system, data acquisition? How you are making sure that it is not going close to that?
Okay, in data acquisition system you are asking, sir? In
the whole redundancy mechanism, by the way the redundancy is executed, the redundant system is executing the operation. How are you making sure that we are not going close to the test article tolerance level of the pressure?
Sir, actually the pressure will be continuously monitored using a pressure transmitter, and it will be getting acquired in either PLC or in data acquisition system in analog input cards that we can monitor in SCADA in PLC as well as in data acquisition system. That will be continuously monitoring, sir. Okay, and continuously monitoring and acquiring. So, and in PLC and the data acquisition system, this logic will be written for detecting based on this pressure parameter. Thus, corresponding safety logics will be executed. Is this
okay?
Did I answer your query, sir?
Okay, so fine.
That's okay. Fine.
I have only just one question from the presentation, whatever you have made.
Okay, sir.
0.7, you told the lower limit. No, you have gone to 0.699, it was responding. EP was responding, am I right?
Yes, sir. Yes, sir.
It was responding. So 0.001 was the pressure value variation, am I right? For it is responding.
Yes, sir.
So I can understand the numerical value, whatever you have given here, but what is the actual thing? This much sensitivity is there for your sensors. All cumulative errors will be there, no? So what will be the error factor, what you have built into this system? The sensor, your PLC is getting the thing from the sensor only. Sensor will be having something. The structural setup will be having something.
Yes, sir.
Some values and some kind of normal variation.
Yes, sir. Total measurement chain error will be there, sir.
From the actual reality, 0.699 may not be the right thing. What is happening there? May be something different.
Yes, sir. Actually, the total measurement chain error as well as this instruments error, if you are considering a total estimated error for this measurement chain, we have estimated to be around some 0.1% of the full scale output.
So have you biased it here?
Sorry, sir.
Have you given the bias to system here for that, or you are not counted? You are not encountered. You are not accounted that here. Have you counted?
No, sir. That is not yet accounted here, sir.
Accounted. So see the problem. What happens now when you keep such this one and response? The system response should be the one which is really matters for the flight or whatever the test article, no?
Yes, sir.
So that should be that should be known to people also. Okay.
Okay.
Otherwise, what is the way of doing that also here? Can you have any actual measurement which can be embedded to the logic here? Can be biased?
No, sir. Actually, obviously, this measurement chain error will be there. We have to account that error here in the measurement.
You are now talking about more of logic here than the actual area. Okay, you are talking. Your paper is about the logic what you built in and implementation.
Yes, sir.
Okay, your focus is on that.
Yes, sir.
Okay. Any other questions? Okay, Masudan, then we can close. If there are no other questions, we can close the session. And thank you so much, Chippy and Karishma, both were good papers, both totally different areas. It was good, both were good papers. One is on the implementation part of exactly what we are doing. That also is actually very important because all put together only the success of the testing and structural system. The first one was on the geometry and second one was on the implementation. Both were having diverse fields from different areas and it was really good. Thank you.
Thank you, sir. Thank you so much for chairing this session. I hope the valuable suggestions given by you would be more helpful for their research. I also extend my thanks to the presenters, Ms. Karishma and Ms. Chippy, for the wonderful presentation. Finally, I would like to thank all the panelists and the attendees for your presence. Thank you. Thank you so much for everyone. So shall we move on to? So shall we move on to the next sessions?
Yeah.
Yes.
With your permission.
You are the rapporteur here.
Just before going into that, there was King Shuk Sen. You are there? King Shuk Sen is there? No. Okay, only the message is that like that one of the author has told that is the last session. Is the last session, and each paper should not be taken before 12:30. He is taking leave only in the afternoon. So normally I think it will come to 12:30. I don't think any problem will be there. I just want to make sure that happened. Harsha, the last session, one paper, Harsha from Boeing, he has told that he can be, the earliest he can come to the session is by 12:30. Okay.
Let them come. We have 4 papers in that session, you know.
Yeah. Just
Here also 4 and another 4.
I want to tell that so that this is taken care of.
Yes, sir. Yes, sir. Our Harsha, he confirmed that up to 12:30 he has a meeting in his office and then he will join from.
So his paper can be taken after 12:30. Okay, fine.
Yes, sir. Yes, sir.
That's the session.
Well, let's go ahead with the next section number 4.
Sir, may I know who's a reporter for this one? Hello, sir. Like,
hello. Yeah, please.
Yes, sir. Yes, sir. Like, I'm asking the reporter for this flight mechanics group.
I'm not sure. You have to ask Kanpur. Vikram Kumar Saini. Okay.
Is Mr. Vikram Kumar Saini available there? Mr. Vikram Kumar Saini, is he available there? Or I think Susan can take this also.
Yeah.
Susan can continue this also, please.
If you have the information with you, please continue.
Yeah, the 4 paper information is there, means you can continue.
I think he also left or what?
No, sir, I'm here, sir.
Okay.
But I don't have the citations.
Doesn't matter. Doesn't matter. I will go ahead.
Yes, sir. Yes, sir.
No, that doesn't matter. Yeah, I will.
Yes, sir. Okay, sir. Okay, sir. I'm starting the session, sir.
Yeah.
So
I'm
Ashok
this
Kumar.
Is. Sir, I will
introduce myself. If you.
Sir, I have, sir. I can.
Okay, carry on.
Okay, sir. Thank you, sir. Thank you. So I welcome you all for the technical session for flight mechanics. It's my privilege to introduce Engineer Dr. Ashok Kumar, sir, for this session. Engineer Ashok Kumar, sir, is a graduate in mechanical engineering, having more than 25 years of professional experience in aerospace and R&D sector. The experience in Indian Space Research Organization ranges from configuring propulsion, additive control systems to the design qualification and supply of rocket propulsion stages. The expertise includes system design, change management, design review, project management, and overall technology management related to aerospace propulsion systems. Positions held include project manager, head of cryogenic stages division, and deputy director of cryogenic stage development project, directly in charge of technical development. Presently is a chairman of IEI Kerala State Center. With this introduction, I would like to ask Professor Ashok Kumar, sir, to say some few words and start this session.
Thank you, Mr. Madhusudan, for introducing me. I think as we have been doing for this entire seminar, we will go ahead with 15 minutes each, 10 to 12 minutes each for each paper, and then 1 or 2 questions at the end of the session. So within 15 minutes, we can close 1 paper each. So let's go ahead with the first paper.
Okay, sir.
Okay, Madhusudan, please continue.
Thank you, sir. The first paper is a novel MOSFET-based single-event latch-up detection, current limiting, and self-power cycling circuit for spacecraft systems. The authors are Mr. Ishan Pandey, Mr. Kinshuk Gupta, Mr. Vinod Kumar, Mr. A.R. Khan, and Professor Sandhya V. Kamath. They are from UR Rao Satellite Center, Indian Space Research Organization, Bengaluru. So the presenter is Mr. Ishan Pandey.
Yes, sir.
Yeah. You can go ahead with the presentation for 10 minutes, followed by 2 minutes of question and answer session. Thank you.
Good morning, everyone. I'm Ishan Pandey from UNSC. This is our paper titled "A Novel MOSFET-Based Single-Event Latch-Up Detection, Current Limiting, and Self-Power Cycling Circuit for Spacecraft Systems." The satellites in space has to experience extremely hazardous radiation environment. Radiation is a form of energy that is transmitted or emitted in the form of electromagnetic waves or particles. Major classification of radiation sources of space are solar particle event. It is one of the most prominent source of radiation, in which solar flare and coronal mass ejection are two main processes which are happening inside the sun. Solar flare is an intense burst of radiation that comes from release of magnetic energy linked with sunspots. The particles emitted from solar flare travels at high speed and reaches Earth in just 10 to 15 minutes. The solar flare are more frequent with increasing number of sunspots, which are periodically varying within 11 years. Similarly, coronal mass ejection are large cloud of particles that are pushed into space from sun's atmosphere. It releases large amount of plasma in interplanetary space. Second source of radiation is galactic cosmic rays. These are highly energetic charged particles, mainly protons and heavy ions, are coming from outside of our solar system. The range of energy of these particles are in thousands of giga-electron volt. The third one is Van Allen belt. The planet's magnetic field trap the charged particles coming either from solar particle events or galactic cosmic rays, which forms a zone of relatively charged particles. This radiation environment of space is responsible for degradation of electronics performance. Here are main effects encountered by electronic components. First one is total ionizing dose. The charged particles travel through material, it creates electron-hole pairs. This is called ionization. Through recombination, the effect quickly diminishes in semiconductor, but in oxide region it accumulates, degrading the performance of electronic components. Second one is displacement damage effect. As it can be seen in the figure, the projectile particle comes from the space and it hits the lattice of our semiconductor devices, which leads to the displacement of atom from its decided position to some interstitial spaces, leads to the creation of vacancy defect. This also leads to the degradation of performance of electronic devices. Third one is single event effect. Whenever highly energetic charged particles having high value of linear energy transfer value, abbreviated as LET, it is a parameter which indicates the amount of energy transferred to the matter on unit distance traveled by the particles. Even a single that kind of particle traveling ionizes the whole track in cylindrical shape. If the path of this particle is somewhere near sensitive region and generated charge is more than the critical charge, it creates single event effect. It includes various effects which can be destructive and non-destructive. Single event latch-up is also a kind of single event effect, especially seen in CMOS or bi-CMOS technology. As it can be seen in the figure, this is the diagram of NOT gate, in which this whole NOT gate is fabricated on a P-type substrate. Here this AND well is made. In this AND well, this PMOS will be made, and here on P substrate, this NMOS will be created. But because of this CMOS technology, some inherent PNP and NPN transistor are created. And this structure is something looks like this, in which both of these transistors stack next to each other. In normal operating conditions, it shows high current in normal operating conditions, it shows very high impedance. But as an energetic charge particle passes through the base region of the transistor, it turns on. Say like nearby Q2, if charge particle is passing, Q2 will turn on. And as a result, the current will be flowing through the Q2. This results the Q1 also turns on. This Q1 and Q2 further drive each other into deep saturation region. and hence increasing the current through parasitic circuit. And this leads to the creation of kind of short circuit path between the VDD and the ground. If the increase in current is not controlled, it may lead to damage to the die. Some of our conventional way to protect the device from this short circuit kind of phenomena are: first one, silicon and insulator technology. According to this, N-well and P-well are made over an insulator, which are further used in making PMOS and NMOS respectively. Due to use of insulator, the parasitic NPN and PNP transistors itself is not formed. However, so that's why this technique is free of catch-up event. However, this process is a little bit costly. Another method is the use of series resistor, which limit the current it provides the safe operation of a device and prevent the abrupt increase in current. But this is not a power efficient solution, because in normal operation also some current will be going to flow to the resistor and it will dissipate the power. The third one is the conventional axial protection circuit, which just detect the axial event and turns off the circuit instantaneously. Here it can be seen in the diagram. For normal operation, this is the current for normal operating devices. Assuming here the axial event triggered, so current will start to rise up. And here we have made the threshold for detection of axial event. So even so afterwards, here the circuit will perform its operation to switch the circuit off. But because of the response time of the circuit, current may shoot up beyond the maximum allowed limit of the die. And there is still a chance exit that device may get damaged with the use of this circuit also. If response time is like enough for the rise of current, so our this device could get damaged. Other one is the use of electric fuse, but it may not be useful for space application, because when it is blown, it can't be recovered automatically. The main idea proposed in the circuit is the use of MOSFET in series with the axial prone device, which would be working in saturation region and ohmic region. In ohmic region, we can see it has very less resistance, while in saturation region, current through drain source of the MOSFET would be governed by this equation. Depending on different gate to source voltage VGS, the value of saturation current can be changed. This is our proposed circuit for axial mitigation technique. It contains these features. The features of detecting this axial event with limiting the current to a predefined level, breaking the circuit, maintaining the interruption time of the circuit, and then recover the power for normal operation. Here in the circuit, we can see this Q1 and Q2, both two MOSFETs are used. Q1 is used as a switch for interruption of power supply to the axial prone device, and Q2 is used as a current limiting element, where this VGS bias is provided. So with this VGS bias, current limit of the Q2 can be set. This comparator CMP1 is used here for detection of axial event. CMP2 is used for power cycling purpose, because the output of the CMP2 is connected to Q1. So whenever this axial event is detected, so major of the voltage will be going to get dropped across Q2. So CMP1 will be having the output high value here, and this R1 and C1 is kept here in order to maintain the proper turn off time is provided to the device. So as a high input will be given here, this will get charged, and as a result, this MOSFET Q3 will be turned on. So because of the normal operation for a long time, this C2 will be charged completely to VDD. Now when this MOSFET Q3 will be opened because of high input, high value of output given by CMP1, this capacitor C2 will be discharged completely, leading the value of the this value will be less than V reference 2. This results in low value in the output of the CMP2, which will disconnect this, which will make this Q1 in cutoff region and hence interrupting the power supply. This is our simulation, which we use actually multi-sync for simulation of our device. The axial prone device is simulated as LED with series resistor and having an SCR in parallel to them. Axial event is simulated with the help of the switch, which biases the gate of the SCR, making it to conducting. The VGS bias of the MOSFET Q2 is varied in 4 different cases of the simulation, and the current probe with the setting of 1 milliampere per millivolt is kept here for the capturing of transient of current. Here our results where different current limits are obtained corresponding to different VGS values. For 5 volt, 450 milliampere is obtained. For 4 volt, 150 milliampere. For 3 volt, for 3 volt around 50 milliampere, and for 12.5 milliampere corresponding to 2.5 volt. This is and after this thing here we can see one thing, that our current is never exceeding the saturation limit. Everywhere the transient is never be going to rise up the predefined level of the current. And the turn-off time of this circuit can be taken as less than 50 microseconds. And the turn-off time of the circuit may vary corresponding to different circuit element chosen. Another feature of the circuit is the auto power cycling. After the circuit is turned off, it has to be maintained in the given state for a certain amount of time, such that the current in parasitic PNP and NPN transistors goes below the holding current. Therefore, to ensure the power turn-off time is provided, some resistors and capacitors are used. Based on different requirements of turn-off time for different electronic devices, the value of resistors and capacitors can be changed. The turn-off time is decided theoretically by this equation, and the theoretical computation of the turn-off time with the simulation result has been computed and is found to be consistent. So here we can conclude that with the proposed circuit, our circuit provides current limiting feature with power efficient solution, ensure the safety of flight devices. The turn-off time can be programmed as per requirement of electronic device, and it has a provision to use with wide varieties of devices. It enhances the reliability of electronic components. Thank you.
Thank you. Thank you, Ishan, for the nice presentation. So the session is open for question and answer.
So Ishan, can I ask you one or two doubts? Have you ever looked at the failure modes of this circuit? Because you are introducing a new thing, totally new thing. They say the MOSFET itself is supplying current to downward systems by adjusting the voltages. Now you are introducing another system parallel to the control device, control circuit, in order to address one of the issue of solar radiation and things like that. How introduction of this affects, or rather the failure mode of this circuit?
Because all these components, whatever we use in the circuit, will be used as a radiation hardened component. So that's why the failure rate from these radiation particles in space will be very, very minimum for all these components which are used in this circuit. For example, here whatever the comparators are used, 88561, this is already radiation red hot comparators. So there will not be any chance for degradation of this kind of thing for this circuit, especially.
I'm not asking about due to the degradation of chips or anything like that. I'm asking the basic configuration of the circuit itself, voltage, current, because there are so many capacities and all that. So discharging them, how surges will be addressed, whether any failures are possible. Some components are failing because C2, 10 microfarad, for example, if it fails, you say it will not fail. That is not correct, you know. So many components you are adding additional into the circuit. So that's one part. Whether you have addressed or not, that is one part. Okay, if you otherwise, please look at it. Second thing is the overall response time of the circuit to protect against the overcurrent downstream systems. What is the maximum time it will be taking vis-a-vis how much the downstream system can tolerate?
Actually, sir, corresponding to our circuit element, but what we have used here, it was not taking more than 50 microseconds.
50 microseconds.
Yes, sir.
And current flow more into the circuit downstream, 50 microseconds is acceptable.
Yes, sir, because the idea here is whatever the response time of circuit would be, the current will not be going to flow more than the this applied this saturation limit of our MOSFET, this Q2. So whatever the VGS voltage we are giving here, it will just put the device into saturation region such that the current limiting will not going to exceed the maximum allowed current of our device.
Yeah,
so
that's a good thing. Okay.
So
there is not going to be any surge because of the introduction of the circuit. That's what you are telling.
no.
Okay, right. Anyway, it's good study, good product for, of course, because it introduces a safety lock in between and avoids a critical failure of the system. Very good. It is. Yeah. Whether your design review, everything is over for this.
Actually, sir, right now just we have made a simulation of multi-sim. The design is still in progress. As we will do it.
Yeah, probably look at the failure modes also in more detail.
Okay, sir.
It's a good study, of course. Good. Thank you, Ishan. We go to the next paper. Any other questions? Of course. I'm sorry. Any other questions? Anybody else have questions? Okay, I think we will go ahead with.
Okay, sir. Sir, Mr. Sasikant is here. He is a reporter. Like he was in the attendees list. That's why he was unable to unmute his mic. It seems.
Okay.
So he has joined now. So he will take care of this session. Sasikant, you can.
Yes. Thank you, Madhu. Thank you. Good morning, everyone. I'm Shishikant, master student from IIT Kanpur. So I'll go with the next presentation. So next we have Shantanu Gulwami from Aerospace Engineering Department, IIT Bombay. His presentation is about circumnavigation trajectory simulation of a lighter than air system in a Venetian atmosphere. So Shantanu, you can please go ahead. Hello, Mr. Shantanu. Hello.
Do one thing. Let us go to the next paper. Ask him to be ready by whatever background work required. Please do that so that he will will be ready as the next presenter.
Okay, sir. Okay. So next we have Mr. B. Venkat Shivram Jadhav. He's from VSCC ISRO Thiruvananthapuram. So his work is about RLV-TD internal pressure distribution, pre-flight prediction, and comparison with flight data. So Mr. Venkat Shivaraman Jadhav, please continue.
Yes. Good morning, sir. I'll be just sharing my screen right away. 1 second. Sir, is my presentation visible?
Yeah, it is.
You can maximize it. It's visible. You can maximize it.
Yes. Okay. Has it gone full screen, sir, now?
Yes.
You can
go ahead. Go ahead. Please.
Good afternoon, everyone. Panelist, session chairman, and everyone present here. I'm Venkat Shivram Jadhav. I'm working in Aero Combustion Modeling Division. This is with I'm in Aero entity of Vikram Sarabhai Space Center, Thiruvananthapuram. I'm working with Srimati G. Vidya, and our entity chief is Dr. V. Ashok. And my topic of my presentation is RLV-TD internal pressure distribution, pre-flight prediction, and comparison with flight data. As you all are aware that RLV-TD was a successful flight which has flown in May 23rd, 2016. And I was involved in the vent scheme design or the vent system design for the entire RLV from inception onwards. So we were able to give the vent scheme design for various compartments, and I did the validation with the flight values which we have got after the successful flight. So I'm just going to give a light on what all went into the design and what are the flight numbers and what are the observations post-flight that we have seen there. So let me start with this. This is the contents of my presentation, followed by the introduction about vent system as well as reusable launch vehicle, followed by the vent system designs, what all inputs has gone into that formulation, and what all vent system is used in the vehicle, as well as the output of the formulation and the prediction and the flight numbers, and followed by conclusion references. So this vent system or the okay, let me start with the reusable launch vehicle. RLV-TD was successfully flown to demonstrate various aerodynamic related technologies, and this wing body configuration is an aerodynamically intensive vehicle, and because of which we had to use all sources of data that includes internet simulations, CFD simulations, and engineering methods to design to come to a conclusive design. And for designing the structure, external pressure is an essential or a crucial part for overall structural design, gust response studies, and flexible trajectory simulations as well. At the same time, the internal pressure, whatever left inside the compartment, is also one of the important parameters for designing the structural design. So, this is where the vent system comes into picture. So we give the venting system so that it can relieve the overall pressure from inside, and it can reduce the overall load on the structure. So the flight pressure data is analyzed and compared with the pre-flight data for venting performance assessment. And this is the typical, this is the mission profile for RLV-TD HEX-01, which was flown on May 23rd, 2016. This is courtesy ISRO website. So this is the typical trajectory of the RLV-TD. So after HS9, in the ascent phase, RLV-TD or the launch or the vehicle is integrated with the HS10 booster, and after it lifts off, it goes up to altitude of 50 kilometers or so, and after HS10 separation, it will be there in the coasting phase. Thereafter, it will reach a peak altitude of 65 kilometers, and thereafter it will try to re-enter the Earth's atmosphere. So this is where we have understood, we have studied the re-entry characteristics of the RLV body itself. And it was very essential, and this validation studies was helpful in understanding the autonomous navigation, guidance and control, and TPS systems, that is thermal protection system, and re-entry mission management. So which will be helpful for our future human mission project also. And sir, as I said, this RLV reusable launch vehicle in the ascent phase, it has attached to a solid motor, which I have just touched upon. And okay, these parts I've just touched upon, so I need not touch upon this again. So in this case, basically the various compartments are involved for the venting process. So as you can see, the nose compartment, fuselage compartment, wings, vertical tail, elevon, rudder, all these things are there. But in studies, the wings, fuselage, nose skin compartment, all are interconnected through internal connections, whereas rudder, elevon, and vertical tails are treated as single separate entities. And we also, in the ascent phase of the flight, the RLV vehicle is connected to the booster compartment or base load compartment through the these wide tunnels, which are shown here. And these fin compartments are also treated as separate ones. So there are a number of compartments which are there for the purpose of venting. Sir, if you see a typical launch vehicle, we have a number of compartments that varies from a payload fairing compartment to a base load compartment, and interstage compartments are also there. So why do we do this venting? Is because as the launch vehicle is at is on the launch pad, when it is integrated, the internal compartment pressure will be, or the air volume which is stuck inside the compartment or in the structure will be at ambient conditions, that is at 1 bar. But as the vehicle lifts off and ascends towards space, the outside pressure will be dropping down. And if the entrapped volume of air is stuck at 1 bar, then the difference between these two will create a pressure differential, and which may cause structural damage if it exceeds the limits. So to avoid this excess loading itself, we'll provide relief, or we call venting, so that it can relieve air at appropriately with through designated vent paths, in such a way that it does not cause the overall structural damage. At the same time, it does not change it does not cause any hinder to the nearby electrical or electronic systems or any electronic packages which sitting inside various compartments. So you can see that, so this is the formulation. This is total pressure acting on any structure. This is common for all launch vehicles as well as for RLV structures. So if you can see this Cp into Q minus Pc minus P infinity. So the Cp into Q is the aerodynamic pressure, which is caused aerodynamic load, which is caused due to various parameters, that is the dynamic pressure and net pressure, external pressure acting on the structure, whereas Pc minus P infinity is the relief or the venting pressure, which is helping to relieve the excess load on the structure. So if the delta pressure or the differential pressure is positive, then it will be taking off the load. Whereas if it is negative, then it will be adding onto the load onto the structure, which will maybe helpful in certain scenarios that I'll touch upon in the coming presentation. So, sir, for any vent system design in a launch vehicle, we need the following inputs. That is free volume of air, as I told earlier. So, free volume of air after integration or the payload after it's sitting inside. The volume of air which is there inside the compartment is the primary parameter for doing the vent design. And of course, vent area. So depending upon the structure, how much area is needed to vent out the free volume of air outside the compartment is another important parameter. And coefficient of pressure at the vent system. So look, like when we'll be placing different vents on the structure, we'll be needing coefficient of pressure at all these vents. And also next one is coefficient of discharge of this vent. So for any typical given vent system, that is a port or a hole or something like a valve, for these configuration, valve configurations or port configuration, we need certain discharge quotient. So we need to assess and we have to find out the amount of mass flow rate which can go from inside to outside. So this parameter is taken care by the quotient of discharge. And the fifth and most important parameter is also the trajectory of the vehicle. So based upon the trajectory, the vent system will be designed in such a way that it does not exceed the design specification. So for all launch vehicle, ISRO launch vehicle structures, the design specification given is the PC minus P infinity, or the whatever you are seeing here, the differential pressure due to venting process should be within the plus or minus 10 kilopascal. This is a common design specification given for at the design process itself. And we see to that our design, whatever design is given into the launch vehicle structure, does not exceed this particular design specification of plus or minus 10 kilopascals. So, sir, you are seeing that coefficient of pressure on the left-hand plot, and these are the typical CP variation what we have observed on the ascent vehicle vent stage. That I'll touch upon where exactly was the CP values there. So that I'll touch upon. And this is a discharge quotient for particular vent system what we have flown in the RLV vehicle. And sir, as I said, yeah. Now in this compartment, for earlier, as I said, that nose compartment or the fuselage compartment and wings compartment, these are all interconnected during the ascent phase of the flight. Hence, these has to be vented out through a common path. So since it is not independent, it is attached to the interstage compartment and again further it is connected to the HS10 motor. So the interstage compartment takes care of the vent system during the ascent phase of the flight. So we are providing venting provision in the interstage compartment. So we had 2 number of cooling hoses which are generally supplied at the launch pad, so that the electronic package sitting inside the fuselage compartment of the RLV is cooled or brought down to the minimal temperature required. So we had that also as a venting system, and we have provided dia 50 mm vent port, or the vent holes were provided in the interstage compartment for venting during the ascent phase. So what all the air is entrapped in the fuselage compartment will be vented out through this interstage. And further down, it is connected to the base load compartment to this white tunnel. So some chunk of volume of air also will be transmitted to base load, and base load has its own venting system which has 6 number of vent ports in the base load region. So this is all a connected compartment studies, and the typical signature is also seen in our conventional launch vehicle vehicles like PSLV, GSLV Mark III, and GSLV as well. If you see PSLV, it is connected from top to bottom through wide tunnels and different distract systems. And for GSLV Mark III also, all LN10 system is connected, and then it is further connected to payload fairing through the wide tunnel, C25 wide tunnels, which is sitting on there. So this is just to give an understanding of how the system works. And as I said, these wide tunnel systems also have circumferential gaps across. I mean, these are not straight tunnels, they have certain openings in between. So those are also considered as venting system for our design. And during the descent phase of the flight, only this RLV part will be flying. So here the venting is given in the base region. So you can see in the base part. So this particular region is what you are seeing in the base region is the venting portion given in the descent phase of the flight. So we have 40 mm dia vent hole sitting here along with the cooling connectors. That is meant only during the descent phase. So both of these will be providing venting. yeah, for venting provision. So, sir, as I told earlier, as the in the ascent phase, as the launch vehicle reaches its intended orbit, the internal compartment pressures will be almost close to zero because it is almost it is has crossed 50 kilometers barrier, and it is 65 kilometers where the pressures are in three-digit number. So it will be less than like 100 pascals or less than that. So at that time, internal pressure will be close to zero. And once it re-enters, if the pressure, if internal pressure is not built up, then there's a chance that the body can crumble due to the external high pressure, which is during the re-entry. So here also we need to provide the venting provision. So this is what the venting system, what we have provided in the base region, gives or sends air into the compartment, making sure that the pressure levels inside the structure is intact. And as I said, pressure is one of the important parameters for our studies. So we have placed 2 pressure sensors inside the bulkhead system with the range point 0 to 20 kilopascals and 22 to 120 kilopascals, just to record the pressure variation for ascent as well as descent phase of the flight. And this is the vent system design formulation. What you are seeing here is a typical compartment. What you are seeing in the figure is a typical compartment with a vent hole or a vent port. So across that vent port, mass flow rate is given through this expression dm by dt, which is again a direct factor of discharge quotient, area, volume, and compartment pressure and density. And so we have our in-house developed software, MP Vent, multi-path vent software, to design for all conventional insular launch vehicles as well as for the special launch vehicles like RLV, as well as for our human space program also. So this software has been used back to back from PSLV onwards. I mean, this has been developed and used in our for all design studies here. And for a typical, as I said, for a typical vent port, mass flow rate is given here. And at the same time, if we are having, instead of one port, if we are having multiple number of ports, this software can cater to that. So this is the sum of that mass flow rate. You can see here, this is given through this formulation. And the differential pressure or the compartment pressure in a compartment will be given is again directly related to the mass flow rate across the compartment. So the sum of mass flow rate added with the other factors, that is gamma factor and internal compartment external pressure at the vents, all this put together, this gives us the internal compartment pressure and differential pressure is computed through that. And this is integrated using 4th order Runge-Gupta method. And so these are the predictions results, as you can see here. This is for the ascent case flight. As I told earlier, the design specification for our vent system is plus or minus 10 kilopascals. So we make sure that our prediction is within that. So with the vent system, whatever you have you have seen earlier in the previous slides, that is 40 mm vent port in the center of the vent and interstage compartment cooling connectors. The nominal prediction values were close to 2.5 to 3 kilopascals, as you can see from the graph. So the top graph, red color line, is the nominal prediction or the differential pressure values, PC minus P infinity, for the RLV structure during ascent phase of the flight. And we usually give the dispersion studies just to make sure that the flight values vary within particular dispersion band, and it varies within that. So we have dispersed the CP, the quotient of pressure, and the discharge quotient. So when we are doing this, we make sure that the pressure is high and the discharge quotient is low, so that internal compartment pressure is higher. And at the vice versa, we will lower the CP values and make the discharge quotient higher, so that more amount of air is sucked out of the compartment, and thereby we'll be predicting the lower bound values. So you can see the blue color values is the lower bound dispersion values. This is the computed values. And what we have observed from the flight is lower than the flight values. I mean, in the transonic, between transonic regime between 1 to 1.5 Mach number, we are seeing that the differential pressure value is highly lower compared to lower bound and the nominal values, which we were not expecting. But at the same time, we had an inspection. We used to have a flight inspection just before the flight takes off. So at that point of time, we have observed certain circumferential opening, that is 1 mm circumferential opening was there. and which can create, which is a possible thing, and it has happened in the flight also. So this circumferential gap will create a high suction area, and because of which air can leak out of the surface. And when we have done including that additional 1 mm area and this whatever the CP dispersion, and then we were able to match the flight values exactly as you can see from the bottommost curve. So this was the observation, and this is similar to whatever I've just told. I just have one backup slide. So this is similar to what we are seeing in the conventional launch vehicle also, sir. So you can see here, this is a typical Gslv launch vehicle payload fairing compartment. So we have a slit region over here. This is the designated vent port region, but we have an unintentional vent area in the form of slit that you can see that this kind of black color marks or the gap, whatever I marked it. So this added on to the CP in that region made the differential pressure values negative. And this is the reason for higher mass flow through the region. And this is the same phenomena which we have seen in the RLV ascent phase of the compartment, RLV phase of the flight. So with that unintentional vent area, we had more amount of mass coming out of the compartment, which led to the negative differential pressure as seen in the figure. But sir, even though the mass flow rate is higher and the differential pressure is lower, the differential overall PC minus P infinity values or the differential pressure values are within the design spec plus or minus 10 kilopascals. So you can see here the it is within minus 5 kilopascals itself. The maximum is around minus 3.5 kilopascals. So this is the values we have observed from the flight. Now coming to the descent phase of the flight, as I said, as it reaches 65 kilometers altitude, the internal pressure of the compartments will be close to 0. And once it tries to re-enter into the compartment, the air has to enter into the compartment, and the pressure should be made sure that it is adjusted to the outside ambient pressure. So the CP values we have considered the base region as shown in the earlier figure. In the base region, we have got CP values from CFD as well as from internal studies. So this is these are the CP values at the base, and based on this, we have provided the vent design. And as per the vent design, it is supposed to go towards the 0, as you can see here, green color curve and red color curve. That is our prediction. But in flight, it didn't happen, because as soon as it reached Mach number 1 and lower than Mach number 1, the flight behavior or the internal compartment pressure trend was completely different from what we have predicted. So this was confirmed by the external pressure sensor also. So it has measured this kind of irregularities, and then after 0.5, 0.8 to 0.5, the external CP variation is as low as -1, as you can see from the top figure. So this behavior, when we have implemented in our vent scheme design and we try to capture that, the differential pressure values also captured the similar trend. So what we have noticed that even though the vent system it is supposed to remain within the design spec and it's supposed to reach towards the 0, as soon as it attained 0.8 and Mach 0.8 and Mach 0.5, it has deviated from the regulated trend, differential pressure trend. And the reason for this is still investigated, because this is an erroneous behavior, and the exact reason for this is not yet known. But by using those external pressure sensor values, we were able to predict the exact flight behavior in the descent phase of the flight. So concluding, sir, I would like to say that reusable launch vehicle, RLVTD is an aerodynamically intensive vehicle which was designed using all three methods: computational CFD, wind tunnel, and engineering methods. Post-flight venting performance in the ascent and descent phase of the flights was satisfactory, as they meted our design specification of ± 10 kilopascals. All the flight measured internal pressure values indicated that they remained within the design specification itself. So flight values in the ascent phase matches reasonably well only after considering the unintentional opening of 1 mm annular gap in the interstage region, whereas in the descent phase, the differential pressure matches with flight values only when the flight measured base pressure values is used instead of CFD or wind tunnel data. So overall, the flight measure pressure compares fairly well with the pre-flight predictions. So these are the references which have been gone into the studies. And thank you, sir. Any questions?
Yeah, thank you, Mr. Venkat Shivanand Yadav.
Yeah, one or two questions I have.
Yes.
This, even though you said in the conclusion that the studies have been, the design has been carried out based on where the CFD and wind tunnel test, etc.
Yes,
But essentially, you have gone by the configuration constraints or configuration requirement. That's what I have seen. For example, the interstage connection below that flight stage, you have ports, when ports would have 40 or etc. located.
Yes, sir.
But I feel it should be more, the aerodynamic characteristics will be totally different in the ascent and descent phase. So some of the ports what you provide for vending during the ascent phase may be detrimental during the descent phase. So do you have some view on that, or number, or do you have are you using some check valves or anything like that? These are the two things I would like to clarify from you.
Yes, sir. Sir, as I said earlier, in the ascent phase of the flight, we have only vent ports or the vent holes which was drilled in the interstage compartment. And that is only, during the ascent phase of the flight, the venting was done only through the interstage compartment, sir. That you're clear now. But after separation, sir, this interstage compartment also will not be there. It won't be there for the descent phase of the flight. So the vent system, what we have provided in the base region is the only way to vent it. To provide the necessary pressure inside the structure. So there we intentionally created those vent holes and cooling connector which is there in the base region. So those were intentionally there during the design phase of the study, sir. And as you are rightly pointing it out, based on the aerodynamic characteristics only, this flight behavior is done. Yes, sir. But we have predicted as per the based on the CFD simulations and wind tunnel studies, based on them itself, we have derived the CP variation at the vent locations, and discharge questions also derived based on those studies, and then we have implemented that. Yeah. So finally, we were able to understand that, okay, our design has successfully flown. There was no disparity except that design phase studies, what I was seen. So that is primarily because of the erroneous behavior of the flight after Mach 0.8. So that is the main reason why it has deviated. Otherwise, our design was full within the design specification given, sir. It is fully validated for the ascent phase of the flight. If you have seen that. So it is fully valid for the ascent phase of the flight. But
you are trying to say that we have seen the match between your prediction and the flight results.
Yes, sir.
Essentially, not on the design part of your system. Okay, fine. Thank you. Anything else?
Yes, one more thing, sir. Actually, these the similar observations as I told earlier. This is a typical payload fairing you are seeing on my screen, sir, right now.
I was about to ask.
So this is vent port, what we have used for payload fairing in GSLV and PSLV type of vehicle. And, yeah. So in the similar type of unintentional vent areas, whatever unintentional areas, whatever I just predicted earlier, there in other compartments of the launch vehicle. So this is the GSLV Mark III X flight. So in that also we have seen this kind of unintentional vent areas, and this has led to the negative differential pressure, what I was mentioning earlier. So yes, this sort of observations are seen in other flights also, and we have fairly validated with our own software, sir, MP Vent.
Okay, thank you.
Yes.
Anybody else have questions? Otherwise, we'll move to the next paper. Okay, thank you, Shivaram.
Thank you, sir. Thank you for giving me this opportunity.
Sir, one small interruption is here, sir. Actually, Mr. KM Kiran Babu. Mr. KM Kiran Babu, are you ready to present your paper, sir? Okay, sir. Okay. Mr. KM Kiran Babu, are you ready?
Yes, yes.
Okay. Thank you. Professor Panta already is here. Thank you, sir. Thank you. Okay.
So let me give a small introduction. So the paper is about the circumnavigation trajectory simulation of a lighter than air system in a Venetian atmosphere. This is from IIT Bombay, sir, Aerospace Engineering Department. Yeah, please carry.
Yeah.
Yes, I'm presenting. Okay. Good afternoon, everyone.
Good afternoon.
Sarkanu Gulwani, and it's my pleasure to present our research on simulation of lighter than air system in Venetian atmosphere, carried out by research scholar Mr. K. M. Kiran Babu and Professor Rajkumar Pant at IIT Bombay. As you know, the Shukran mission by ISRO is planned in near future. Am I audible, sir?
Yes, yes, you are audible.
Okay. Yes, so the Shukran mission is planned by ISRO in near future. And according to the Venus flagship mission study report, is the aerobot systems, that is lighter than air systems, are perfect for carrying out atmospheric dynamic studies in the upper atmosphere of around 50 to 60 kilometers. And if you look at the horizontal scale, the requirement is the global circulation and the global measurement on the Venetian in the Venetian atmosphere is required. In this region, it happens to be the atmospheric properties comparable to that of Earth, and the materials are available for balloon systems. In the previously, there have been multiple missions to Venus, and among them, Vega balloons have demonstrated the flight of balloons in the Venetian atmosphere. And from these missions, various atmospheric properties had been already collected. And from the measurements that were carried out by previous missions, a Venus International Reference Atmosphere model is developed by NASA, which we initially planned to use for these atmospheric simulation studies. However, there are certain limitations of this atmospheric model, in that the latitude and longitudinal variation of atmospheric data is missing, and the wind components in this region are also missing. Therefore, we approached Dr. Sebastian Labonis of LMD Lab and Dr. Prashant Kumar of Space Application Center and obtained the general circulation model data to have a atmospheric variables and the wind parameters in 4 coordinates, namely altitude, longitude, latitude, and time Venetian in the Venetian atmosphere. And this atmospheric data was interpolated in 4 dimensions with the linear interpolator to couple it with the trajectory simulation. Coming to the superpressure balloon, the superpressure balloon is usually partially filled at the launch, and it gains the float altitude at its design volume. And in our current model of trajectory simulation, we have also considered the thermal heat transfer that happens because of the atmosphere on the balloon film, as well as lifting gas. So we first developed the trajectory model for Earth balloon, and we validated it with the Hasi balloon flight. And then we adopted the trajectory model for the Venetian atmosphere. So from the sizing point of view, based on the variation in diameter, the float altitude varies, and the lifting gas that is carried on board maintains a superpressure in the balloon, and a particular ascent rate is determined by the lifting gas. Here we are considering the launch altitude of 40 kilometers and nominal payload of 45 kg. Since 40 to 60 kilometer is the interested band of altitude in the Venus, and we are here showing the variation in the balloon diameter that is required to achieve a desired float altitude for a given scientific payload mass.
Yeah, please proceed. Any problem? Got
Hello,
stuck up
Mr.
or
Ashok.
what? Yeah.
Maybe any internet issues, sir.
Okay.
Mr. Ashok, are you there? Mr. Ashok? Mr. Ashok, can you hear us?
Ashok Kumar, you mean Ashok Kumar?
Yes, Mr. Ashok Kumar, sir.
Yes, I am able to hear you, but I'm not seeing anything on the screen.
No, sir. Like the presenter, sir. I mean, Ashok,
Shashikant. Shashikant, right?
Yes. Kiran Babu, sir. Kiran Babu. KM Kiran Babu, sir.
Yeah.
So, sir.
Mr. Kiran Babu, your presentation is complete?
No, not yet, but some issue is there.
Let's wait for a minute. Maybe he's rejoined.
Yes. Actually, Professor Rajkumar S. Pant, he has also joined from IIT Bombay. He has another paper. So I'm waiting for him also.
Yeah, what is happening?
So maybe he's taking it takes time, but also we don't have next presenter also, sir. In fact, Mr. Jitendra Singh from Rajiv Gandhi National
Again
Aviation.
IIT Bombay.
Yes, sir.
Excuse me, I apologize. There was a network problem at my end.
Yeah, Mr. Ashok, please continue.
May I continue, sir?
Yes, please. We are waiting for you.
Okay, sir. May I please know where I left?
Next slide. Next.
Okay, sir.
This kilometers 40. Yeah, this one. 40 to 60 kilometers.
Yes. So therefore, the sizing problem was of interest here, where a particular scientific payload that need to be carried for a desired float altitude, how much diameter of balloon will be required? So with the increase in the desired float altitude, diameter also increases in this fashion for helium gas. Trajectory model for carrying out simulation of the float phase, which is essentially the circumnavigation around the planet. For that, we had to convert the Cartesian coordinates into geographical coordinates, and similarly the vector quantities for velocity were converted from zonal wind, meridional winds, and vertical winds into Cartesian system. We finally got the circumnavigation trajectories. The balloon was released from 50-kilometer altitude and at 3 different latitudes and 0-degree longitudes. It was observed that the revolution in the northern and southern hemisphere covers more area, around 2 circumnavigation it completes, so 2 revolutions. And finally conclude that we developed the trajectory simulation framework and validated the trajectory with the Hus balloon experiment. When Venus balloon is when superpressure balloon is flown in Venusian atmosphere, it covers area in the proximity of the launch of its latitude, and therefore it will require multiple missions of superpressure balloon to explore more area of the Venusian atmosphere. Thank you.
Thank you, Kiran Babu, Mr. Kiran Babu. So the question session is on.
Any questions? Okay, I think we will go to the next paper then.
So right now, Mr. Jitendra Singh is not in the cruiser. I mean, not in the panelist.
Professor Pant will be sharing that paper.
Okay. Okay.
Is he available, Professor Pant?
So just before he was, sir was there here, but right now I don't see him in the panelist. So.
He's just joining.
Yeah. Okay.
Dr. Rajkumar S. Pant.
Hello.
Yeah. Hello, guys. Professor Pantji, please go ahead.
1 minute. Hello.
Yeah, Professor, able to
Hello,
join.
I would like to know if I'm audible.
Yes, you
I'm
are audible.
there in the meeting. Okay.
Yes, sir. Yes, sir.
So then shall I share my screen? Okay.
Yes, sir. Sure, sir. Sure.
Okay. So very good morning to everyone. I'm Professor Pant from IIT Bombay. And my colleague Jitendra Singh, unfortunately, well, he was supposed to present this paper, but I will be presenting on his behalf. So first of all, I'd like to start by giving you a bit information that the stratospheric airships about which I'll be talking in the next 10 minutes or so are essentially the ones that operate at a height of around 40,000 feet. Okay. We normally deploy them at 65 to 80,000 feet, which is the 20-kilometer to 17 to 20 kilometer range. And that is because the wind velocity there is much lower than the values. We can notice that at around 40,000 feet where we have the jet streams, you can see that they are operating at very, very high winds. So the applications of these high altitude airships or HAA are very diverse. They range from military as well as civil roles. And this particular presentation is going to focus more on the military role. Right. So you could call this airship or a blimp as a high in the sky, which allows you to focus on any of the objects below. And for every role, we can have multiple candidate missions. The resurgence of development in the area of airships started in mid-85 when they came back from oblivion. But in the early 90s, the usefulness of persistent surveillance that airships can provide got into prominence. This is the artist concept that shows you the size of the airship as compared to some other contemporary aircraft like the E-3 Sentry or E-8C or the Global Hawk, which are used for surveillance today. So we noticed that the blimp is quite large in size, but it is at a fraction of the cost of the other platforms. Now, as we are looking mainly at military and paramilitary roles this presentation, and we notice that several applications can be tackled by the use of high altitude airships. And in the current scenario of our country, when we are grappling with the two unfriendly neighbors at both the edges on the western side as well as on the northeastern side, immediately one can look at any of these boxes as a relevant application for the high altitude airships. There are many similar roles, but I'm not going to focus on that much today. I always say that applications are generally limited by imagination. Now, many people would argue that since we have satellites and our country is known for very cost-effective satellite deliveries, then why are we looking at airships? The reason is that we are going to make this airship behave like a low-altitude geostationary satellite. As you know, the satellites which are geostationary normally fly at very, very high altitudes. And because of the huge distance, we do not get the required amount of clarity many times. And low Earth orbit satellites have a better clarity, but then they are not able to maintain station. So the major advantage of an airship, a high altitude airship over satellites are listed here. To me, the most important one is, of course, the cost, but also the important thing is that airship can be brought down to reconfigure it so that as technology on the ground improves, we can refurbish and send it back up, which we cannot do so easily with satellites. Once a satellite is launched, it just keeps on performing that function, and the technology on the ground becomes obsolete, or then we just have to live with it. Okay. In the Indian context, there are many, many applications. We could cover our entire country and the sovereign borders of the country using just a handful of aerostats or high altitude airships. And for military and paramilitary missions, there could be applications which are the need of the hour, as mentioned in this particular slide. Even when you look at civilian applications like resource mapping or supporting our other activities from safety point of view, refineries, etc., you can see that there are many, many possibilities. And also, it can be relocated. Okay. It can be relocated so that it can monitor the area of interest. And this I already showed you that areas of interest can be covered by a swarm of high altitude airships. In the context of our neighbors, you can see that the Karakoram range and the Kargil zone is an area where there is a huge requirement. So if we are able to position and I have already achieved over the sovereign territory of the country, you can see that with two of them, we can cover almost the entire area of interest to us on both the Chinese front as well as on the Pakistan front. To focus more on the Karakoram highway, which is the connection between China and various cities in Pakistan, location of a system within the line of control or within the Indian territory or Indian controlled Kashmir territory easily can allow us to look at what activities are happening and take decisive and preemptive action much before the activities become difficult for us to manage. Similarly, there are other areas highlighted here in this figure which can be monitored very easily. There are going to be many stakeholders when this system is developed, and almost all agencies of importance, about a dozen of them are listed in this particular slide, which will have a huge stake in the deployment and operation of high altitude airships. In the development of the high altitude systems, again, agencies like DRDO, DST, CSIR, and ISRO are going to play a major role. And the academic institutes like mine also has got a huge role, because we can be instrumental in looking at the big picture and developing the required technology. So quickly we can go through the status of high altitude airship development globally. We are not the only ones who are looking into it. The whole world is looking into it, whether it is Korea, Japan, USA, UK, Europe. Okay. So here is a list of some of the airships which are under development, and the target values for India for high altitude airships determined by discussion with various stakeholders are mentioned in the last line. So we notice that this is going to be a huge animal with around 250 meters length and 60 meters dia. We're looking at a payload of around 2000 kg, which could be multiple type of elements, and it is going to be very large in size. But then there are lots of issues and risks which we have to handle. There are several technologies which need to be mastered and developed, and there are also certain areas in which we are behind, as I will elaborate in the slides as we go ahead. So the question that arises is, all this is okay, but does India need a high altitude airship? Okay, definitely we have a need, and more so in the current scenario. So what are the technologies which have to be developed? First of all, the basic envelope itself at such a large size we cannot use the existing materials which are very heavy, and also the fabrication techniques have to be improved. You cannot carry any conventional power plant system for a long endurance application, so we need to look at solar powered systems with regenerative fuel cells. As we have already done, a lot of aerodynamic configuration and optimization studies are needed for the full-scale development. The control of the whole system has to be mastered. Launch and recovery of such a large body is going to be a problem. And remember, it has to also go through that location of very high speeds. And we have to also develop the required payloads to do the mission that is required. So in the next few slides, we are going to just highlight, based on our study, what are the technological jumps required. So for instance, the target fabric that will go on this airship should less than 100 grams per square meter, or GSM as we call it. And in India, currently, we are looking at around 250 to 300 grams per square meters. The pioneer in this particular area is ADRD in Agra, the DRDO laboratory, which has done a fantastic amount of work in the development of technology of LTA systems in the country. They are the leaders. They are the leaders in this technology in the country. But they need to be given a lot of support and encouragement, because the requirements are that we need to improve material by 3 times, we need to improve fabric strength by 2 times, and permeability is going to be a huge issue. Okay. Similarly, on the solar cell front also, we need 20% improvement and 4 times improvement in the power density and the watts per square meter. Especially looking at solar cells, many challenges, and lot of research is going on in the country. We in IIT Bombay also are working on developing these kind of cells under one of our National Center for Photovoltaic Engineering. If you look at the regenerative fuel cell technology, we are far, far behind the current requirements. The estimated value DARPA wanted to develop is 800 watt-hour per kg, but what they could only achieve was half of it. And we are actually around 8 times below that in the current information. So that's we have some research projects going on, and we need to do a focused project. I'm actually unable to give more than I have been. So with that, I'd like to stop, and I'd like to open the floor for any questions that you may have.
Helium permeability. Hello. Helium permeability. Any metal coating inside the fabric or anything like that can be considered?
Yes. First thing I want to clarify is that for such a large platform, we cannot think of using helium as a sustainable manner, because
I think some issues again.
Yes, sir, some network issues and sir got disconnected.
But he is not aware, I think. He is continuing probably.
I think there is a problem here.
Yeah.
We are losing the connectivity. I'm
Yes, sir. Yes.
right now. I think I'm just saying that helium is not going to be a sustainable solution for such a large airship. We definitely have to go back to hydrogen as the lifting gas. Even though there are dangers in using hydrogen as a lifting gas, we all know that people are very scared. But there have been several studies done, even in IIT Bombay also we have done experiments in the field to show that handling of helium, if done very carefully, can be considered as an option. Because if you go for helium as a lifting gas, then your system is going to be almost unsustainable from the point of view of logistics and refurbishment. So the question that you asked about permeability, yes, permeability can be handled by either coating the material with suitable substances, or even by using lightweight metallic films as barrier films. But bear in mind that we are looking at very large surface areas, so therefore we have to look at the cost and the weight implications. Did I answer your question?
Yes,
Sure
yes. Okay, thank you. Then anybody else? Any questions? Dr. Venkatakrishnan ji?
No, I was just listening. It was a very interesting paper, actually.
Yes.
Yeah. I was just listening what, no, it was a very interesting paper.
And may I just use about a minute of the time to talk to you about an interesting activity. So this area, lighter than air systems, is very new in our country. Apart from ADRD, Agra, there are very few people working in this area. So what we are doing is, in association with the Institution of Engineers, I'm very happy and proud to say, we are conducting the first international conference on design and engineering of LTS systems, which is going to be held in the month of June in IIT Bombay. And if you please allow me, I will quickly just show you the web page of this conference. It's called as Deltas. Design and engineering of LTS systems, Deltas. This is going to be held in IIT Bombay. We are hopefully going to be doing it in the physical mode, not in the mode that we right now. We are hopeful that it will happen in the physical mode. And interestingly, several experts from all over the world have signed up to participate in this conference and to come and join us. We have already received a large number of papers to be presented. And one very interesting thing is they're going to conduct an indoor airship flying competition as part of this workshop on the last 2 days. Okay, so please do check for delta 202 202.in, and it would be nice if a large number of you can.
Again, the connectivity is lost, eh?
Yeah.
Yes, sir. Yes.
Actually, a lot of things could have been discussed. Could have discussed.
Yeah, this is a very, very interesting area. That's what
very futuristic
paper.
paper.
Okay. Something at least not new to me, so I was just listening.
Yes,
No,
sir. Sorry is back again.
Yeah, a lot of technologies are required.
Yeah, I'm sorry. The connectivity is a serious issue today for some reason. But as I mentioned, I will actually put it in the chat window so that.
Yeah. Please put it so that now people can contact you. Yeah, your email and contact you. Please put in chat box so interested people may contact you.
Right. Unfortunately, I don't see a chat window. I only see a question window. The organizers can probably
you have
just
Q&A, no Q&A.
Yeah, I do have a. So I'll probably just. I don't know, facing issues today. Yeah, I'm back in the meeting now. So yeah, there is a Q&A session. So I cannot ask a question because I'm supposed to be presenting.
So in the permission section, we need to activate that. Right. In the security section, we need to activate.
Anyway, if you can just give a simple Google search on the name of Design and Engineering or Deltas, 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 you will get it, sir. Otherwise, my email address is very simple. My name is Raj.
Okay, I think we need no point in
waiting
further on that. We will get delayed. We will get
delayed.
delayed.
Get delayed otherwise. No,
Yeah,
we can chat box.
And
we can see the otherwise deltas. We can see your website also and continue.
Yeah. So we will thank you, Professor R. Pant ji from IIT Bombay. So it's a really good paper. In fact, a very futuristic paper as far as we are concerned. So thank you very much. And you are unfortunately we could not really enjoy your presentation because of the connectivity issues. But then thank you very much. So we are at the end of this session. I thank you.
Yes, we are done with the.
Thank you, Shashikant, for as rapporteur, and also
yes, thank you,
and also Mr. Madhusudan, who helped us in the first paper. Thank you very much to both of you, and also the presenters of the 4 topics. Thank you very much. We'll close this session.
Thank you, sir.
Excuse me, sir. My name is Harsha. I'm from Boeing. Is there a session planned for me? I think it was moved to 12:30. I received an email.
Harsha, your paper is coming only in this session. Only it is coming. Okay, as per normal, it can come in. I think this 3rd paper in the new session. Okay.
Yes, it is second paper. Second paper, sir.
Second or whatever paper. Now, as per this your session is just starting, so we can continue as per plan. No?
What time, sir?
Just starting.
Because I'm in office, so
just starting. No, lunch will be after this only. Okay. So
okay, sir.
What we have decided is lunch will be after the technical paper. Then after 1 hour gap or 3:30, not 1 hour gap. 3:30, whatever may be the time. 3:30 will start as per the plan. The validity function. Okay.
No, morning we said 2:30. Am I correct?
No. Just now Vivek Astana called and he talked to DP Misra. Since it is declared already 3:30.
Okay.
But I think this will go some more time. This is now 12:30. No, this will go some time. By the time you take lunch and come back.
Sorry. Okay, right. Take care.
So this can go as per plan. No issue. This fourth design and system engineering and Ramraj H. Sundarraj is either.
I am here, sir. I am here. Good afternoon, sir.
Good afternoon. So you can start now as per the normal plan. 4 papers.
Yes, sir.
As per the list.
Yes, sir. Yeah. Good afternoon, everybody. Welcome to the last session. The theme is design and system engineering. There are a total of four papers here, and let me first introduce the chair session chair, Dr. Venkatakrishnan PV. Dr. Venkatakrishnan graduated with a master's and PhD from IITM in the year 1989 and 2006. He started his career as a scientist in propulsion in a complex ISRO. And over the course of his career, he has worked in various aerospace manufacturing and material development. He was previously deputy director LPSC and also deputy project director the Gslv Mark III. He has a long list of achievements, awards, accolades that he has earned over the last few years. In the interest of time, I am not going into all that, sir. That's a very long list you have, and it is really amazing. But in the interest of time, I'm going to cut short that, sir, and say, sir, thank you for going.
Thank you, Ravna. Then you can continue with the session.
Yes, sir. So let me call the first paper, a modeling cognitive workload of air traffic controllers, Mr. R.S. Pant, sir. See there's Pant, sir.
Raspand only was presenting last paper also for previous session also, no?
Yes, he was there.
He's knowing that this session is preponed and he is immediately coming, no? He's supposed knowing, no? Yeah, as per original plan, after this was lunch actually. But
yes, sir. I'm not sure whether he is aware that.
Can anybody call him and find out whether he's there? Because this connectivity also was lost in the last when coming.
Okay, sir. Towards the end.
If you go to the second paper, you can ask him to come
back. Second paper, Harsha, are you there?
Harsha was speaking.
Can you start, Harsha?
Yes, yes, I am here. Am I audible?
Please start, Harsha.
Yeah, sure. Let me share my screen quickly.
Okay, sure.
Just give me a moment. Please let me know if you're able to see my presentation.
Yeah, we are able to see. No issues.
Okay. Yeah. Okay. Hello all. Thank you for hosting me on the 34th National Convention of Aerospace Engineers. And compared to all other papers, which are purely technical in their nature, here I present a very simple presentation based on system engineering. I mean, before that, my introduction is I'm Harsha from Boeing, India. I work as the lead engineer on structures, and basically I work for the test and evaluation stream in Boeing. So here I present a methodology which we recently used for a document management system, which was built internally within Boeing, and how we use the systems approach to define the project and also to realize the project as per the internal requirements. So let me go to full screen and get in. So a brief background about why the conceptualization of this aerospace document management system. was that we had a lot of documents which pertain to aerospace, particularly the testing documentation. And all these were distributed in various different directories. It could be like a shared drive, or it could be on local desks of individual laptops, or it could be on SharePoint and many other places. So accessing all of them when it became, I mean, when it was pertained to a particular project was quite difficult for us. Like if we immediately want some input data, we have to go to a separate browser and download the data for that. And all were not intertwined with each other. So engineers had to depend a lot on other teams to get all the data what they required. And what we realized was that there was a lot of time spent on these activities. So here there's a list of the documents which were digressed or which were shared on different platforms. We had the input documents, we had the test preparation, what we used before the start of test and what we used during test, and finally what we release post-test documentation. So the concept was to bring in all of these data together onto one single platform so an engineer can go and download or even access all of these documents in a single go. So what we did was we adopted a typical 5-step methodology for conceptualizing this system or a project or the project. First one is to identify the needs through stakeholder analysis. I mean, we had to do a lot of brainstorming sessions with the end users, that is what we call as stakeholders, to understand what exactly were their pain points in the present system or present state. So, and then what after that, we had to define the requirements post the analysis, what exactly our system should contain or consist of. And then step 3 was how our system will perform. That is how to define the performance, what is desired out of the system, what we design. And finally, the penultimate one was that we have to design actually the interface where all these documents can be stored, and design, which is under the design, solve, and improve category. And finally, we have to test this new system before releasing it to the end users for their usage. So we had to do the verifying, testing, and also reporting, like what exactly we have done as per this step to our stakeholders or our leaders, so that they will give a go ahead for the actual release. And the current state, what we did through stakeholder analysis was when we interviewed them, we found that there is no single repository for storing and release of these documents, and they're distributed, as I mentioned. The second important concern was that the traceability of the documents were not there. That is, somebody creates a document and they route it through email or any other.
Arsha, you are on the first. You are on the first slide only. Am I right?
No, sir. I'm in the 4th slide.
No, it's not moving then for me at least.
Oh, is it?
Yeah, can you again once more? You can do it so that it move. Now it's moving.
Is it? Okay, then
current state has come.
Okay, sir. Fine. I think then I will stick on to this view itself. If I go to the full screen mode, it is not showing up probably.
This is okay.
This
is
okay, sir.
Readable.
Yeah. Sure. Okay. So sorry about that. I mean, if I have to just take you through the other slides quickly, this is what I was talking about, the various documents which are being stored or which are being used during testing, and also the 5-step methodology, which I just mentioned about. So, okay, coming on to the current state. So the second point was that the document traceability was not there. That is, each and every document, particularly in aerospace, have to be traced. That is, who was the creator, who was the author, and who was the one who approved, and finally how it got released. So all this metadata should contain within the document or the system which stores the document. So that was currently not so effective. And third one, the signatures and document approvals were performed separately. That is, we send an email to the stakeholders, sending the document, and they give their concurrences. So this was like a repeated step where we have to follow up with the stakeholders with repeated follow-up emails. So there was no automated process for the document approvals. So this system, what we wanted to do, had to contain the documented signature approval process inbuilt. Then notification to stakeholder, that is, if any document is getting modified, or say we have released as a new revision. So we are using or releasing a new revision, that is Rev A or Rev B. So those notifications should go to the stakeholders who were involved earlier as part of their document creation, because they need to be aware, and their responsibility lies there. So the existing system did not have such an automation process. And finally, these documents, when it was shared with external vendors, say, when I say external vendors, it could be manufacturers, or it could be test labs, or it could be even the regulatory bodies like FAA and EA, say PISA. So how they use our documents and where they are flowing down these documents, we had no clue about it. So that is the reason we also wanted to bring that also online within our system. So to understand once it is shared externally, what is the traceability of our document. So these were some of the major points we listed down as the current state, that is what was there previously, into a desired state, that is what we actually want out of this newly developed system. That is, we will have a common repository which will contain all the documents as a single platform for document storage. Then document details of creation and modification, that is, as I mentioned, the traceability and modification details have to be tracked every time it is done. Third one is the signature and document approval should be embedded within the system. And finally, notification to stakeholders for creation modification of the document will be there. And all of this will contain the system to trace back when it is shared externally as well. So these are some of the common pointers, and we just noted this as our first step in define requirements in the systems engineering language as an integrated platform, which will be having the unified platform for document storage, then the metadata recording, then the approval, signature and approval, and the notification, and also access with data security, that is a configuration control. Then post this, how do we specify the performance of our document management system? The integrated platform, if we read it as a cyclic flow, we will be checking in the documents, that is, we'll be starting to store the documents in this integrated platform. Once it is stored, then it will undergo a review, that is actual review by the stakeholders. It could be the technical leads, it could be the manufacturing engineers and other people who are involved in the regular approval process. So they will initially review and provide a feedback if in case any changes have to be made, and that will again go through this cycle like a closed loop. And post that, it will be pushed to the approval stage, that is, it is mostly a signature stage. By this time, the document would have matured enough to be approved by all the stakeholders. Then it will get released formally in the document library, and it will undergo a configuration control. That is, it will be assigned the version number and the revision number. And finally, it will be given access as to where it has to be, or rather who can actually view and download these files. So this boundary is for the integrated platform, what the function it does. And the external things are like, where is the actual document being stored, though it is with the integrated platform, but we need something which stores the document like a cloud storage. Then review and approve basically is done by the reviewers and approvers who are external to the integrated platform. The document library again is integrated with the cloud storage, where it is actually getting released and it's a separate portal. And finally, the configuration, the metadata generation, the version control is being accessed outside, and also external stakeholders will be defined who can access, and that will be done externally. So this basically is the flow chart of how our system performance had to be undertaken. Yeah, this looks a bit crowded. But nevertheless, I'll just briefly discuss about one of them, and then I think the rest of the things are similar. And this is not exactly the way we have put across in our organization. We have a proper user interface, but unfortunately, I could not get the approval to share that externally to any other this forum. So that is the reason I've just put up these block images to just share what we have done. So in this integrated platform, as we defined all those requirements, we had these basic 6 modules which were developed. One is for the documents, that is the document, if at all a new document is to be created, or upload an existing document, check in a revised document, and finally download for all stakeholders if they want to download a copy of the document. So the review process of the document, where we assign stakeholders, we put an end completion date, when do we need the document to be reviewed, then what is the priority, and then finally, after all these inputs have been done, route it for review for the stakeholders. Then approve, similar to review, where the signatures will be done. And the release, where once all the signatures are done, then the release process happens, where the document is available as a release document. And for configuration control, once this is checked in, the document will be assigned proper numbers and the versions, and that will be visible as metadata. Finally, access, where we will provide as to who all can access these documents. So what we discussed previously, the same thing, but in a user interface format, where the end users can actually start using this platform. So that is what it basically looks like. And once we designed, I mean, as this module mentions, design, solve, and improve. We solved some many issues, and then we gave it to beta testers within our team, who tried to use this and found out a few fixes or bugs, and then we had to improvise on them so that everything was sorted out. So that is this basic step what we did. And post this, we also undertook a verify, test, and report phase, the V diagram, that is verification and validation phase. The improvise here is a part of the V phase, where initially we did as the 5-step methodology, we came to system build, and once system build was done, we did the database testing, individual modules. We did not combine everything together to test. We tested stage by stage, initially how the database access is working, then the storage access, then the encryption, and finally all the modules put together, how it is working at a system level. So that is what we did in the validation phase. And as I mentioned, the beta testing happened, then it was released to a minimum crowd. Then they also started using and testing on a day-to-day basis. And again, we found out some bugs. We fixed it up. So we made it as though it is good to be released for the larger audience, where hundreds of people will be using it. And only then we released it for the entire team. So this was basically how we developed this entire system. And finally, a few conclusion pointers and what we are intending to do as future developments. Conclusion, though systems engineering is used for very complex systems like a spacecraft or a rocket launch vehicle, so we also, as our organization policy, we want to use systems engineering in the minutest of the projects, so that we can actually define anything and everything as a system, and it gives a proper methodical approach for handling a new project. So that is what we are aiming to. And it was very helpful for us in defining various components of the system. As I mentioned, when we went through the 5-step methodology, we were able to specify the system performance, what we or what was needed. So it helped us in defining them. And also the V diagram helped us to define the stage-by-stage testing. Otherwise, all put together in one go, maybe it would have been more clumsier for us, that at the system level acceptance. So stage-by-stage definition helped us to improvise step-by-step and finally reach a full system which was capable of handling all the document storage. A few limitations of the document management system. It is not so recommended for smaller organizations which handle less amount of data, because I think a company like Boeing or any other large organizations which have tons of documents, typically they face this issue of the document management or the configuration control. But for smaller organizations, if they have to employ, they should have sufficient amount of data for this to be employed, because it needs a dedicated team which has to be formulated for the DMS development. As we saw, we initially thought of doing it like within the team, but then we had to involve a lot of software engineers for coding, for developing the UI. We had to borrow resources from other teams. So then we finally thought that we have to have a dedicated team for this, for the successful implementation, and that we have given to the management as feedback. So smaller organizations, they'll be again having overheads to have a dedicated team for just managing a few amount of data. So it is not so recommended. And implementation of DMS across enterprise requires time and efforts, because basically there'll be always an inertia from the employees or the end users to have something new or to accept something new. So that has to be broken. And it took us a lot of meetings to actually convince people of embracing this new approach. So that cost us a lot of time and effort. And also repeated push from management and other things have to be required for this. So we faced a bit of glitches there, but anyways, now people are quite happy with the new system. And also proper training to end users. We spent a lot of time training batch by batch to make people understand this new approach, and also how they have to use it as a step-by-step guide. So we provided them with user guides and also troubleshooting guides. And we also were online most of the times, especially with our US counterparts who log in the night India time. So we had to be there for them to support them in case they had some glitches or they had some issues. So that was a bit of limitation. But I mean, it is just with our organization. But overall, these are, I don't say actual limitations, but these are some of the challenges which will be involved when it comes to the DMS implementation. Future work, we are thinking of adopting blockchain for enhanced data security. We are in talks with the blockchain team within Boeing so that they can leverage the security features of blockchain for configuration, particularly when it is going outside Boeing, and also the traceability. And the next version, what we will be doing, we'll be using the model-based systems engineering approach for defining requirements. As Mr. Madhavan was mentioning yesterday, the chairman HAL. So MBSE is going to be the future. Most of our teams are embracing this, not just the document management, but of course, all other teams are trying to use the MBSE approach, where we will have a model-based centralized approach where all the requirements which change will be flowed down automatically to the end users, and the loop keeps happening. So the core teams will be knowing what is happening within the system, but otherwise in systems engineering, a paper-based systems engineering, it is not so effective, because if somebody makes change, the other person may not be aware of that. So a model-based system will always help in driving those changes all throughout. And that is what we want to have in our future work. So this was what we did. And also we though this idea is pretty simple, just like how to put up the documents in one particular system and manage it, but what we estimated, or rather we found out, was that we saved up to 1.3 million US dollars by doing this system, because of the previous system where people had to access a lot of from all different sources. When we brought it into one source, the time consumption was reduced so drastically that we were able to save 1.3 million US dollars for the program. And this was highlighted to our CEO level also. So this was one of the major accomplishments which we did as we were from our team last year. So this was the benefit and the impact of this document management system within Boeing. With that, I conclude my presentation, and I am open for questions.
Thank you, Harsha. It was different altogether because you are all aware that when it comes to manufacturing, when to translation to reality from drawing to and documents to systems, and especially companies like Boeing, which supply chain going across the continents and countries, and other countries also, systems when if they are not in place will can really cause a lot of harm to the product as well as this actual final product, and all these things are very important. One thing which I would like to share here, because one is that what you told, systems implementation can make huge profit. That's one message you have given very clearly here. The profit is not by sales alone. The lean manufacturing always from Japan and all, they have addressed that value engineering and all. They addressed actually the product and product related features only. System related features can add value to engineering, and lean manufacturing can contribute to manufacturing. It's one important concept what we have followed, forgotten actually. Here, you are told very clearly that by implementing the system, you've got a huge profit. And that is one message what people have to carry, because for a system which is in place is equal to a robust company actually, because people can change and systems can continue. That is the importance of systems engineering, which you have very clearly given. Second thing, we have a problem in ISRO, which is we have got such systems in ISRO also, no issues. But the problem is when you are giving to supply chain, we are not able to extend the same to our supply chains, and because more than 50-60% of the items are being now done by our supply chain partners, wherein the raw material continued to be issued by ISRO itself, because that is an important thing which they can't purchase, and because source purchasing for them in lower quantity will be very difficult for them. So in large quantity, for getting this quantity discount, we purchase it and supply to them. And once that is going to them, whatever strict control we are having in the stores, as well as stores issue vouchers, so many things documented, unless they are not following it properly, the entire effort what we have taken is lost. So how to extend it to the supply chains across and see that they are also using the same system and same thing. And if we have some problem also, once something is issued to one supplier, and if some other supplier for same component is finding it extremely difficult to make it, and he has got some rejections from one center to another work center, supply chain work center, we have to shift the raw material also. For that and all, if you implement the system, it will be easy to implement whether anything is left over in the some other work center. We can see from the computer and PC itself on desktop itself. So it's an extended logic I'm building, but very difficult to implement. But we have to work for all these things. Okay.
True, sir. So just to add on there, in Boeing, what we typically do is that our system, however it is getting displayed, even the vendors will also be viewing the same system, but they will have to log in with a very controlled access into Boeing systems, and also their access to the documents will be limited to what only they will have to work upon. But that will become as a unified interface for both the vendor and the OEM, so that whatever they see, the vendors also can see. So this becomes a very common platform. Otherwise, the distinction cannot be made sometimes by vendors.
But unfortunately, in our country, the vendors are not that educated to come to this level of. They feel it's so sophisticated, and the architecture and access, limited access given to them and all. Many of them doesn't update the items. So they will start, but they won't update continuously. That's the problem. What is happening?
Absolutely, sir. I totally agree. Yeah, this is what even we faced when we make some design changes. At the shop floor, they might drill a different hole, but that will not be reflecting on the drawing. Just to accommodate, they will do that.
Even the drawing is not update immediately. They are not doing it. Okay.
Yeah. So, I mean, not to put things down, but in Boeing, that is taken very seriously, because anything they have to do on the shop floor, they will have to raise a request before doing anything. So that is how we will trace any changes made to the part, which has to be taken permission from our chief engineers or approved engineers. Only then they'll be allowed to do some changes. Even if it causes a delay, we are okay with it.
There's a different type of culture which has to come along with the whatever technical thing we are doing. A culture.
Absolutely, sir.
Culture we call it. That is what
Absolutely,
we all should actually work for, and that is an important thing. What we have to see that such a thing is created in India, along the aerospace manufacturers. The aerospace culture has to creep in and to sustain also. Okay.
Yes, sir. Yeah, and because we are a zero defect industry, not like Six Sigma, we can't even sustain 1 part in million defect. We are a zero defect industry, so all these things are very much essential, because it will cost us something huge when neglected.
In Boeing, I have one doubt. Your manufacturers are allowed to take up work from commercial industries also, or will
Yes,
be
sir.
restrained to aerospace alone?
You mean Boeing itself will be taking Boeing vendors?
Vendors.
Okay. A lot of our commercial aircrafts, we have vendors, sir. I mean, if you take a typical aircraft, there are minimum 10,000 vendors for a single aircraft of Boeing across the globe. So, I mean, the vendors are also categorized for the commercial and as well as the defense, because the US restrictions come into place, the ITAR restrictions come into place. So vendors are categorized accordingly. However, in India, we are having a lot of vendors who are coming up, because as I said, these are some of the basic systems which Boeing employs. The vendors who can adhere to these systems are only getting onboarded, who can be mature enough to for these strict quality control and other things. Only they can come up. So, but in the past few years, because of this Atmanirbhar Bharat and all, Boeing is encouraging a lot of Indian suppliers who are supplying to the actual aircraft. In fact, there is one joint venture called Tata Boeing Aerospace Limited in Hyderabad. It's called T-Ball. And in that, we are manufacturing the entire Apache helicopter airframe. That entire production line was shifted from US to India, and we are catering to the global requirements of that particular fuselage. So everything is getting manufactured in India.
Okay, thank you.
Good. I think we will go stop there in the interest of time. Sorry about that, Harsha.
Thank you. No problem, sir. Thank you so much. Thank you for accommodating.
Thank you. It was a nice paper, but different paper.
Yeah,
thank you so much. Yeah.
Thank you, sir.
Thank you.
We go to next one.
Are you there? Are you present? Are ready to start? Rashmi?
Rashmi
Yes,
was
sir.
there, no?
Yes,
Yeah,
yes.
yeah, please.
Yes.
Please continue.
Yes, sir. Sir, my slide is visible?
It's visible. Please continue.
Yes. Very good afternoon to all of you. Myself, Rashmi SS, working in structural design and fracture analysis section as a section head in Vikram Sarabhai Space Center. And my topic for the presentation is design through analysis approach, employing more than one software for design finalization industry structures of 410 class launch vehicle of ISRO. And the paper is co-authored along with Srimati Rachel, retired head lower stage structures, and Sirajuddin Ahmed, group director, structural design and engineering group. And to this forum, I'd like to give some introduction about how the structures, aerospace structures are. And we demand for the high performance as well as a lightweight. And the roles for these structures are to withstand the loads as well as the environmental corresponding to environmental condition. And this structure also to provide a housing for the payload, propulsion, guidance, and control systems. And these factors to be considered for the launch vehicle structures are the structural integrity, low mass construction, ease of fabrication, of course, low cost and high reliability, and as well as the high strength and stiffness. And coming to the industry structures, we have primary as well as the secondary.
Sorry, but the slide is not changing.
The first slide is still continuing. No, the same problem. I think you can just come back again once more. Yeah, now it's going. Now it's moving.
Yes.
Okay.
Thank you.
And now it's visible, right?
Yeah, visible. Yeah.
This is I was talking about the interstage structures. Different type of structures are available. Basically, primary structures as well as the secondary load-bearing secondary structures. Primary structures are only always load-bearing structures, and which provides the structural strength, stiffness to the launch vehicle. And secondary, of course, we required for which are not subjected to the aerodynamic and primary loadings. And depending upon the loads, nature of the loading and all, we may have the failure modes of the structures. And these structures are interconnecting the different stages. And of course, the loads acting on the structures are axial force, shear force, and bending moment also. And this is an exploded view of the launch vehicle. What I was talking about, the different stages connecting interstages are there. This here you can see the one stage is about first stage, second stage, and third stage. And in between the stages, we have the interstages. And we have different type of constructions are available, like monocoque, closely stiffened, isogrid, waffle, etc. And monocoque, just like a similar to an eggshell, we have a skin alone. And if you are strengthening with the ring structures, ring stiffeners, and as well as a longitudinal stiffeners, we will have a closely stiffened construction. And if you are going very close to the stiffeners, then closely stiffened structures. And there are the equilateral triangles of arrays of ribs are there. So these kind of structures are isogrid structures. And this here, basically, it is effective in resisting the tension, compression, shear, as well as the bending loads. And there are closely closed isogrid as well as open isogrid, where we are using as a vended interstages. And coming to the typical design cycle of an interstage, we have after finalizing the specifications, we should have a plan for the phase of the conceptual design. And right from that, we should have a basic structural design. And of course, design checks are involved. Then along with that, we have to validate through the design by using the finite element softwares. And we have a different softwares we are using in ISRO. And with the help of that idealization and analysis, we have to improve the designs as well as the specifications of the objectives of the designs are met. If it is meeting the specification, then we may have to go for the final phase of the design. And again, the detailed FE analysis called for, and we have a detailed model for the three joints we have to go for. And after all these things, we may have to release as a design drawing. And all this cycle involves the reviews, proper reviews, addressing, and the design drawings are involved. From there, we may have to fabricate the structures by giving the corresponding tolerances and all. We have to fabricate the structure to meet the schedules. So all these things involved a very good team effort, including not only the design team, otherwise project activities, then fabrication team, then designs, drawing support. Then hardware realization also will, we have to validate our design. Of course, one method is to analysis only, but for analysis also, we have to validate through the structural qualification test. Then only we can go for the flight readiness of the structures, and we can qualify the structure for the flight. And there are different interplay in between the designs are there. Design involved, as I said, the environmental conditions are involved, then load, temperature, then structures, configuration, efficiency, analysis, and materials. So there are interplay between the designs. Design materials, design structures, structure materials. That is, design structures and materials are interrelated, because we have some particular load only we are designing the structure. We have to consider about the lightweight as well as stress, what is available, or what is depending upon the material we are choosing, what should be the limitation of the stress we can go for, and without any failure mode. And in our team, we have designed almost so many structures are designed by the interstages of the Matrix structures: SSN, CNC, nose-cone adapter, strap-on nose-cone, then interstage one dual, then intertank skirt structure, which is sitting between the two tanks, then core-based rod structure, that is twin engines are placed on the core-based rod structure, then core thermal shroud, lower frame structure, then S200 structure also is strap-on based rod structure, STS structure, like that. All so many structures we have designed, and because of the time limitation, we have only talk about the two structures, that is one dual structure and core based rod structure. Coming to the interstages of the structure, this one dual structure configuration itself, right? I have touched upon the different type of constructions are available. Closely stiffened structure is this configuration type, and this diameter, of course, a 4 meter diameter and 1.6 meter height, made up of aluminum alloys. And this right side indicates that our structural configuration, and this structure most of the structures will be having the different planned cutouts are there for taking out the propulsion systems. So many activities, all these things, whatever we are seeing is a helium gas bottle placed on the structure. For that, we have to give support for the inside the structure also. So these things, some bottle things are the helium gas bottle, and these wires has to be taken out. So these only all these cutouts are introduced. Some will be about the wire tunnel cutout, and some will be the acting as an access cutout. So we may have to design up accordingly, and we have to, depending upon the lot of the software, lot of analysis support also required. And this, and as I was telling is, initially I was touching upon the loads acting on the structure. Each structure we have a separate definite kind of loads, axial force, bending moment, and shear force will be there. So we have to go for the test. So we have to derive the loads. What are the structural loads we have to qualify a structure. So there are in this structure we have to do a structural qualification test for the equivalent axial, one compression load. Then there will be a tension load because of the tensile load and bending moment acting on the structure. And there sometimes we may have to go for a variable axial load or an equivalent axial load. So here I have just touching upon some examples related with this. So how we are deriving a load, how the FE analysis is supporting for the our full qualification level. And this is a representation of the FE model for the this much area of the vehicle. And these are the other structures, and this is my area of interest of the structure, and this is having a connection between the tank as well as another structure. And we have a different kind of loads available, like axial force, bending moment, shear force acting. All these are indicated by the red arrow marks acting at this. And this is a zoomed view of the pictorial representation of how the loads are acting. And we can see in the next slide, we have that interface. These are the flight models. Flight model, of course, we will have an adjacent structure cutout and all will be there. And these are the, whatever this indicates in the cyan color is the fastener load distribution. That is the interface load distribution acting on the structure. And this structure will have some difference in compared to test case. Also we have to do test. We will simulate the adjacent structure affected by the another aluminum interface ring and all. So we will not be having any cutout effect. So it will be a very smooth thing. So these are the specific features we are using from the software is MBC force extraction for finding out the faster load. So we have to match with this flight conditions to the test. So that only we can prove that our interface loads are also meeting the specification. And there comes a different software. We have a expert in all, so many softwares are available like Pattern, then Nastran as a solver, then Abacus, then NISA. Then we have an in-house developed software of the FEAST, finite element analysis for structures. And so we were also able to, if it is with the softwares are brought out items and we have to be paid for each time manual maintenance and all. So we thought of doing in this analysis also as a comparison with the in-house developed as a Make in India policy. So this is a representation of the FE model in that finite element analysis software. And these are the loads we are applied, like in our whatever we have seen in the structural test setup. Similarly, some jack loads are applied. Same loads are we are applying in that FE analysis, and the boundary condition also applied. And there are different kind of number of, depending upon the shell, beam, and all stringers are idealized as a beam element, and shell as a shell also there. Then interface fasteners are modeled as an MBC, whatever I have told earlier. Like MBC connections are there to find out the interface loads. And these are the comparisons of the out of 3 load cases when we are touching upon. And these are the comparisons with respect to the finite element software FEAST. We have a comparison of the displacement, a resultant of 1.32 versus 1.3 in the Nastran. And analysis also 1.32 for the comparison of the axial versus 1.3. And this is also against the stresses comparison. And this corresponding to stress resultant von Mises stress. And these are the circumferential stresses. And next case, we are touching upon the tension condition. We have a comparison for the tension condition also. 5.1 as a deformation against 5 in the Nastran package. And this versus stress comparison. And cutout also, it is basically we have to see the cutout strain nearby. We should not exceed the capacity of the material. So we will have monitoring the strain, our structural qualification time also. We used to have a lot of measurements to know what is the actual stresses acting on the structure and deformations also. And this for one example for the variable axle load, I was mentioning about the bending moment acting on the structure. This we sometimes you have to go for a variable axle load also. And at that time also we got a good comparison, and we have experimental setup also planned to measure the cutout strains nearby, and we got a reasonable good match with the prediction from the most of the softwares. And this was the overall comparison of this one dual structure, the displacement and the cutout, whether it is opening or closing. We may have to think, we may have to predict, as well as the measured values also we should find out. And these informations are required for finalizing so many even so many plans later also. Sometimes we may have to place some motor inside the structure. So this contraction, how much will be the contraction? So depending upon that, how much slot we have to plan. So all these things are required for our future things. So we will plan accordingly to measure all the deformation, whatever possible from the one test itself. Because one structural qualification test itself, hardware making, then test setup making, then structure, so many powers are involved. So we have, and time also involved. So we have to find out, we have to get the maximum output from our test itself. And coming to the CBS structure, this is basically one what initially I was touching upon the closely stiffened structure only. So here this structure consists of a cylindrical portion of a closely stiffened one and an isogrid conical portion of the this left side indicates the CBS structure. And these two engine, whatever you are saying, is placed on the aft ring of the structure, because this is a twin engine, and this twin engine will be acting as a local load, concentrated load, and this local load effect should be should not be directly coming over here top, because the top is interfaced with the other tank structure only. So we have to get a uniform distribution of the forend of the structure. So we have to be, our designers' job is to should not concentrated load should not go, and as well as this structure has a housings of many of the engine packages also, and this controlling the controlling that yaw plane actuator as well as the pitch plane actuators are there, and these cross indicate here only this yaw plane actuators are placed, and the middle plane as well as the other pitch plane actuators are also placed over this to control the engine deflections. And these locations where we are mounting the engines, we should have a stiffness criteria also, because the displacement is very much essential to know how much the structure should deflect, how much radial deflection is there, how much axial deflection is there. Accordingly, we can plan the controls on the control for the vehicle. And so we have to have a software comparison of all the things. Why we are doing is we should have a confidence on our analysis as well as a test how it will, and this will be a good idea of how much this can deflect. And this is a comparison of the FEAST, NASTN, and NISA also. And each analysis was done by expert in that software. And these are the displacement comparison. Again, this is the radial deformation. We right now I am telling about stiffness is a matter for the structures, about the CBS structure. And this is stress comparison. And the displacement comparison versus NASTN, NISA, and FEAST, and stress is also compared. And we used to have so many measurements in that structural test, what I was indicating. So the strains also, we can get a comparison from this. And from this, we can infer that the maximum displacement matches very well between the three softwares, and the maximum strains also have shown a good, reasonable, well match during the qualification test. And as a conclusion, I could say the design through analysis approach in the design finalization industry structures are summarized for only 2 is mentioned due to the time planned for us. And it has been seen that when the test results a reasonably good match with the qualification were also correlated by the digital image processing near the cutout of interstages. And indigenous software use is also comparable with the commercially available software. And as an acknowledgement, I could tell CS Somna's Secretary, DOS and Chairman ISRO, he was only successfully spearheaded the Mark III mission as a project director, and his support for during the design phase realization and the qualification test is acknowledged. And the present director, Nikishan sir also, and deputy directors of structures entity during the design phases, and present deputy director Krishna sir, and Beena madam, head of my division. And other because it is a teamwork, we could not acknowledge, we have to acknowledge the other team involved in this testing agency, then experimental mechanics division. Then of course with the support of the so much of reviews and all these things can be critically reviewed, and suggestions only needed for their entire analysis qualification stages. And the paper is anyway reviewed by the Associate Project Director, Space Transportation System, VSSC. And as a and one more thing I could able to tell, the contributions by the Venkateshan sir during he was a deputy director of Mark III time for the, at that time only material procurement, fabrication, trial rolling during the design phases we used to and I would like to thank you also, sir.
It's over. Then it's open for questions. Any questions from anybody? I think audience would have got a good flavor of exactly how the structures are being designed. And Feast is one software. Feast now non-linear is functioning now.
Started, sir.
It is
non-linear is
qualified.
It's not one part only there. Other part it is going on.
Okay.
Yeah, one question.
But for structural qualification of our structures and all, we can able to get most of the industries are able to get a match with the Feast analysis.
Okay.
Now your study, your comparison, is it a part of an exercise to validate the Feast software, or?
Yes, sir. We are giving input to them also because it is a good translator also. Because being as indigenous software, we should always give a support to them, and how we have to whatever problems we are facing. So we can, if we are executing, then they are able to solve the issues also. So it is one way that Feast software also will get developed.
Validated. Okay.
Stages come now to use only Feast. Can you dispense away with other
softwares? That's what my question is. That's my question also.
The time will come, sir, because only now the non-linear and part of some of the things they are able to solve it, and some now we have to compete with the other software also. But for our problems, I think we can able to manage with the Feast software. Nowadays,
we have to identify the corner cases where it may not be valid at all. Probably, I don't know. That those also have to be identified and tested and validated with the other software, Astra and all other things. Then only we can say it is fully usable.
Yes.
Yeah.
Now that
anyway, it's a continuing exercise as we go further.
And all the structures are also going to be a part of the Gaginian mission also, all the structures.
Okay. All the best for you.
Any other questions from anybody? Okay, it's not there. Thank you so much, Rashmi. It was a good, nice presentation. Of course, going back to some years back for me also, because Corby showed us all these, or Therma showed and all. Fine. Thank you so much. And whether our other paper, one more paper was there, RS Pant, has he come back?
He has not come back, sir. Sarthak is here, sir. Sarthak Solar.
Hello, yes, sir.
Yes. Will you be doing the presentation on behalf of RS Pant?
Okay.
Yes, sir.
Okay, then.
Okay.
Then
so I think we can.
That is the last paper, no, in this session, I believe.
No, sir. After that, there is a paper by.
Okay. One more. Yeah. Fine.
Additive manufacture. One question.
Yeah, additive manufacture. Yes. Kanpur IIT.
Yeah. Yes, sir.
Ram Kumar. Yeah.
Yes, sir. So let's start with Sarthak now, sir.
Yeah, please.
Sarthak.
Yes, I'll share my screen.
Please do, and don't use the full screen mode, please. I think that is causing some issues.
Is this okay?
This is fine.
Can you just only the slide is moving, other one slide is not moving. Okay.
Yeah. Okay, okay. It looks good, Sarthak. Can you please start?
You can continue, yeah, please.
Sure. So hello everyone, I'm Sarthak Solat and I will be presenting a research study done at the Department of Aerospace Engineering and the Department of Humanities and Social Sciences at IIT Bombay, which is titled Modeling Cognitive Workload of Air Traffic Controllers. Now, before jumping into anything, let us look at what is cognitive workload. So workload is a multidimensional, multifaceted construct. We cannot explain it with respect to a single parameter, even 2 or 3 parameters, but like it is something that cannot be observed directly. We have to infer it from apparent behavior and psychophysiological processes. For the sake of our study, we have abided by the definition given by Wickens, who refers cognitive workload to the dynamic relationship between the resources needed to carry out a task and the ability of the operator to supply those resources. So basically, it is the relationship is of the kind of a supply demand type. And also our main approach to model this cognitive workload is to include 2 broad factors, one of which is the system factor, the another is the human factor. But then the question arises is, why do we need to study workload for air traffic controllers? Well, with automation and rapid rising technology, we have seen a major shift from physical activities to mental activity. Now, most of our execution jobs are now replaced by jobs. And even the sector of aviation has seen a continuing growth throughout history, which leads to an increase in demands of ATC services. So like we need an increase in capacity of airspace, which can be only possible through adaptation of airspace design. And like to assess these design interventions, we need to understand the relationship between the air traffic controllers and their cognitive workload as it affects the efficiency and working of the controllers. Now, ATC has 2 main goals. Number 1 is efficiency of the task, and number 2 is safety of the aircrafts. So like much of the modeling work that is done in cognitive workload in respect of ATC is like categorized in 2 ways. One is the generic open loop model, second is the closed loop model. Like as we can see in the open loop model, it has a mediating factor, like the air traffic factors. The mediating factors are the ones such as the ones we are taking, the human factors, system factors, etc. Talking about closed loop model, it says that the choice of work method, etc., regulates the input work further in a feedback loop and affects it again, so that the output is affected by the strategies employed by the controllers. And like as you can see above, I've written cognitive workload equal to system factors plus human factor. To expand, system factors are basically of 2 types as well: airspace factors or complexity, and operational constraints on the task. Like operational constraints are the ones like restriction in airspace due to weather, etc. And complexity is obviously we can model complexity as the number of aircrafts currently in the airspace, the traffic density, etc. In human factors, we can take factors such as age, skill, strategy, attention, memory, IQ, and so on. Now, there are different ways of assessing cognitive workload. There are these 3 methods: subjective method, performance measures, and physiological measures. What we have used in our study is the eye tracking method. Now, the eye movement parameters and the association of cognitive workload are as follows. Now, pupil diameter, blink duration, and blink rate are kind of self-explanatory. But what are saccades and fixation? These are 2 new terms. The saccade, like as you can see in the right figure, there is a circle and there is a line. So the circle is what we call as fixation. The line is what we call as saccade. So fixation is where we fix our gaze for a longer moment of time, And saccade is when we quickly move from one fixation to another. So these association with cognitive workload are like, if pupil diameter increases, the cognitive workload increases. Blink duration decreases, the cognitive workload decreases. This is the relationship, as we can see the up arrows, down arrows with cognitive workload for these respective eye movement parameters. And now what we have done in the study, how we have collected the data and what analysis we have done. It's like data of 56 controllers with varying age, experience streams was collected, and like we analyzed them with their eye movement data. Now the original experiment for collecting data was done in the psychophysiology laboratory of IIT Bombay, wherein like a single ATC simulation task, which was of like 40 minutes, was given to the controllers, and then we recorded their eye movement data. Now we also developed a pupil load index so that we can profile the cognitive workload, and pupil load index was calculated as the maximum percentage change in the pupil size. And like to further analyze the data, 3 different ways of distinguishing these groups, like based on the arrival rate, experience and stream of controllers was devised, and the data was analyzed accordingly. Now, what is arrival rate? It is basically a proficiency. One second. Arrival rate is basically a proficiency metric, like which means that high arrival rate equal to high proficiency, which can be translated to a higher level of expertise. Just having a negative correlation between pupil load, like as we can see in the result, we have a negative relationship between pupil load index and arrival rate. This gave us the conclusion that increasing proficiency of controllers leads to decreasing workload. So we can expand this idea and reach to the conclusion that expert air traffic controllers face lesser cognitive workload than novices. We were also successful in modeling workload for a trainee batch of controllers, which gave an R-square of 0.67. And this is the relationship as shown in the slide. The other set of results and conclusions that we reached were related to the fixation duration and saccadic amplitude. So now increased fixation duration is a metric of high engagement. Like as we saw in this slide, if the fixation duration increases, it means that the cognitive workload or the not the cognitive workload, but the engagement of the controller with the task increases. So now what happened is we had a negative correlation of fixation duration with age, experience, and time. Now what this means is that like with increasing age, experience, and time, people are less engaged with the simulation task. And this is with respect to the air traffic controllers. Now the reason for this could be like either of two sides. For example, we can say that maybe older and experienced controllers have less motivation to do the experiment than the other novices, or perhaps with more age and experience, the task at hand seems to be automated in the mental system of these controllers, like that they don't have to engage much at the task at hand themselves. For controllers taking more time, they can feel fatigue and lose engagement with the task, or maybe they are just doing the task in a more relaxed way, so that they are not much engaged with the task, and time is also consumed in completing the task. So like for experienced controller, fixation duration is negatively correlated with arrival rate. This goes on to show that experienced controllers have low engagement with the task, and maybe this is because it is too easy for them, or because they are lacking the motivation and disinterested. Like there are two explanations for this one particular result. As saccadic amplitude is concerned, its relationship with human factors show that controllers with high experience have larger visual scans of the airspace. Like as we saw, saccadic amplitude is the distance between the two fixations. Like when we move our eye quickly without fixating it at one particular location. So if it shows that having a positive correlation with age and experience shows that with elder people and highly experienced people have larger visual scans, like they scan their screen or whatever much more and have much less fixations while solving the task. Now, the reasons for this would be the strategies employed by the controller. We'll see what different strategies could be employed in the later slide. But like, yeah, having a quick conclusion, what all we have achieved is like a batch of trainee ATCOs were created and we modeled a cognitive workload for that. A relationship between expertise and workload was established and metrics affecting engagement with the task and visual scanning strategies were found. Now, for future work, it would be interesting to investigate more factors pertaining to skill and strategy, which could give us strong differentials in individual capacities, resulting in strong correlations with cognitive workload. More experiments also need to be done, specifically manipulating the data to find the answers of engagement and visual scanning strategies of ATCOs. And future research could be done to analyze the dynamic aspects of workload with better human factor tools, which help to access differentials in controller capacities. Thus, like we can make a stronger workload model. Towards the end slide, like this is just a display of different types of beautiful visual scanning patterns formed by the controllers, and this is for the same simulation task which was given to them. So majorly these four categories were the one in which the strategies were employed by the controller for the same task. So yeah, like with this I end my presentation. Thank you.
Thank you so much. In fact, totally, as I told some time back, no, Pant also was having a totally different domain last time also when he presented. This also is a totally different picture, but all associated with aerospace and aeronautical sector. So definitely, it is a very important subject actually, and you touched upon the right subject and the right workload perspective of the ATC and their kind of thing also. A new subject, I think the audience will be, I think, interested in at least knowing exactly if any gaps are there, whatever you perceived right now during his presentation. It's open to questions now. First of all, let me thank Sarthak for a totally different presentation. At least I am new to this subject, as I told some time back, once the last presentation also. Okay.
Modeling human factors into mathematical equations, very complex. And I just would like to ask him, as this Sarthak, how do you model the training aspects of, say, two people trained in the same class will be absorbing it differently and reproducing them differently. So how do you model that part into air traffic controller? Because experience training alone has been getting into your model, but the way people take it,
yes,
how do you
sir.
model it?
So basically, like for human factors, we use 4 factors based on the metadata which was available of the controllers. And like these 4 factors were, one was age, one was experience, and one was time taken by the controller to complete the task. Like these 3, and the 4th one was, so like this, what we did, we had the age, and in experience, we had the years. So how many years one has done. Like for there were novices as well. For them, the experiences were 0 years. Like we took them as 0 years. The third time done to complete the task, like it was a 40-minute task, but some people completed it in 30 minutes, in 25 minutes, in 45 minutes, and even 50 minutes. So this was one of the factors. Like we could see, like with time, does having, like solving the problem in a larger time span, does it affect the controller to face more fatigue, more cognitive workload or not? So that was one, and one was arrival rate. So arrival rate
Okay.
is based on the sequencing.
So your experience, you are converting into tangible form. That's what I would like to know from you. Like,
Yes.
yeah, okay, thank you.
No, it's a dynamic factor, of course. One model, what you have created with experience, zero experience, and other things, and whatever you're having right now, for a time frame today, will not be the same for another time frame after 5 years, because even you are telling the age, maybe 50 years back age, whatever you tell may be totally different from today's age what you're talking, because totally different things have changed a lot, sir. So whatever you're doing should be highly dynamic and continuous process. Okay.
Yes, sir.
The model should be continuously updated, otherwise no, it won't be having relevance.
Yeah, yes. And even the air traffic controller undergoes technical modification changes, you know, which makes the process easier for the air controller. So I like that. Okay, fine.
Even technology impact also may be there in future.
Yes,
with our space assisted navigation all coming into picture. All these things will totally a different scene after some time. Maybe even aircraft navigation may be totally satellite based aircraft navigation and all are coming now. So totally after some time it will be a different picture altogether.
Yeah.
Okay. So thank you so much. If there are no other questions, Sarthak Solat, it was a nice presentation and a totally different area. And we can move on to the next presenter.
Yes, that is the last paper for the day. From IIT Kanpur, Prasenjit Sharma.
Yes, sir, I am present, sir.
Yes.
Fine. Please continue.
Yes.
So I am sharing my screen.
Please.
Sir, is my screen visible, sir?
Yeah, visible. Please continue.
Good afternoon, sir. Good afternoon to all. Sir, myself, Prasenjit Sharma. I am a PhD student at IIT Kanpur Department of Mechanical Engineering. So I will be talking about the status of additive manufacturing in the aerospace industry. This is how it will go. First, I will talk about the introduction of additive manufacturing, and then we will go into the additive manufacturing in aerospace industry, and then we will talk about the design optimization for application, and then we will look through into some of the major application of additive manufacturing in aerospace industry, and we will have some a brief discussion on cost analysis of additive manufactured product. And then we will go into the challenges and how the current trends is going, and then finally I will conclude. So lately, sir, additive manufacturing has become a very hot topic, most top subject in the aerospace industry. Unlike traditional manufacturing, additive manufacturing can be defined as a incremental layer by layer manufacturing from a CAD model under computer control. However, ASTM has defined it as the process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to those subtractive manufacturing or conventional methods. So, what it basically provides, I will go through the features like design flexibility. Layer-wise fabrication approach enables additive manufacturing to manufacture parts of almost any level of complexity with a very less material usage and reduced mass. With cost of geometric complexity, what I mean is with complex designs, there is no need to additional tooling. I mean, refixturing, increasing expertise of operator, or even manufacturing time. So there is no additional cost included. Dimensional accuracy. Most additive manufacturing machines have capability of several hundreds of millimeter of tolerance, and additive manufacturing are also capable of producing single part assemblies, products that have integrated mechanism. The parts and joints are printed using support structures which are suspended in air. It is then removed in post-processing methods. So basically, I will not touch in the post-processing methods, but With post-processing methods, it makes very useful. Additive manufacturing is very useful in aerospace industry. And it has a very no tooling exercise required, on-demand and on-location manufacturing reduces inventory cost, little wastage of material. So it can also be considered as a sustainable and eco-friendly manufacturing. So the capabilities lens, light engineered net setting, ultrasonic consolidation, bad polymerization. These are all the processes which enables functionally graded parts. Specific material properties like hardness, flexibility, stiffness, adhesive properties, and color on basis can be designed. Physical working models, articulated models, complaint mechanism, locomotive robots, and prosthetics, including variety of pre-assembled parts and fully functional components like joints, tightener, flexure units are manufactured using additive manufacturing technology. Embedding foreign components, what I mean is the components like sensors, circuits, motors, threaded rods are embedded into a part as it is being fabricated. Embedding can be done by deposition, manufacturing, ultrasonic consolidation, CNC accumulation, material jetting, and even extrusion process. Combination of additive manufacturing and deep direct writing technologies. It is basically used in signal routing, conformal electronics, discrete electronics, 3D antennas, force sensors, magnetic sensors, strain gauge sensors. So these are the fields where printing of circuits and sensors can be done. So basically how it works, first the model is conceptualized, and then it is model is generated, CAD model, and then it is converted to STL file. Then slicing is done. Then we set up the machine, parameters, materials, whatever it is, and then fabrication process printing part starts. And the removal here, it is the post-processing technique which I was talking about earlier. I mean, removal of support structures, hot accelerated phase for removing porosity. So these are the process which we do, and then the final part is ready to use. So in additive manufacturing is used almost in every sector, but what it is important to look at, the aerospace holds 18% of its manufacturing is done by additive manufacturing. So this is the data which is being collected from research papers. There are a lot of methods which are being used. So we will compare 4 methods which are being used in aerospace industry. One is laser powder bed fusion. These are for the metallic parts, electron beam powder bed fusion, wire arc melting, and laser metal depositing. So every process has its own advantages and disadvantages. So when you see like wire arc melting, very less accuracy. However, the laser powder bed fusion has a very good accuracy. So we have given us marking like how accurate. We have given marks on 10, that how accurate on different parameters like complexity, accuracy, surface finish, overall cost saving, material utilization, post processing requirements, mechanical properties, flexibility, maximum volume. So these are some of the parameters which have been used to compare these techniques. So now we are moving towards the topology optimization. The topology optimization is the algorithmic process of optimizing a mechanical component or part, usually through material reduction. This is calculated according to mechanical stresses the part is subjected to during regular function. It can be categorized as a subfield of or a broader field of a structural optimization. So the main benefits include less usage of material, a sorted design process, maximum performance. So how it is done for lightweight structures. So there are basically 4 stages which is included, like preparation of data, topology optimization, to-resist adaptation, and finite element analysis. So at this stage of data preparation, the definition and sorting of load cases are very important for obtaining strong and reliable parts. The definition of technological and technical constraints for parts no less important. All this data will be specified as different parameters and setting in topology optimization software. At the topology optimization stage, creating of the design space is very important. After that, an iterative topology optimization process begins, which consists of directly from technological and finite element analysis testing of result, and if necessarily changing to topology optimization parameters. So at the topology optimization result adaptation stage, fast and qualitative creating of the optimal CAD geometry is generated. The following method can be used: creating parameterized 3D geometry in CAD, or non-parameterized bionic geometry using splines in special hybrid modeling software, and STL editing for rapid analysis of result and prototyping. In conclusion, at the stage of finite element analysis, an important design is required to complete or modify the design process. This methodology is well proven in the design of aerospace parts, basically because of the lightweight structures. So additive manufacturing opens up a lot of opportunities previously unable to traditional manufacturing. From the point of design, it is become possible to use a bionic topology of part, internal channels for cooling, integration of parts and functions for efficiency in weight, cost, and assembly, lattice microstructure for lightweight and use in medicine application also. At the same time, due to complexity of the additive manufacturing technological processes, the use of additive manufacturing is not always cost efficient. To increase the cost effective of design and production, it is necessary to use special techniques of design for additive manufacturing and optimize an additive manufacturing technology process. At the design stage, the initial part or assembly must be redesigned, taking into account the advantages of additive manufacturing and the capabilities of machines. In the case of success, redesign of the part will have a unique characteristics. We will look into the cost operation lately. So here is an example topology optimized part. So this is an engine bracket with casting constraints. So I am not getting into detail, but what I wanted to show is that when the performance of the bracket doesn't reduces even though the material has been redistributed and the design is being optimized. So this is another example. So this is the application which are being used. See the complex necessary for this is also an Indian bracket. Just now I was talking about this is a customized production. This what additive manufacturing provide is on-demand manufacturing. It has a very high performance to weight ratio. However, there are certain challenges associated with them, like size of the parts. Like it is difficult to print bigger parts. Scalability of the parts are very limited material, and obviously the cost related to these, and the inconsistent quality, because the standardization of the build additive manufacturing build part has not been yet done. So some major applications, like there's a hydraulic manifold for aerospace. These are printed, 3D printed. There's a lightweight titanium structure printed by EVM process. So when we talk about the advantage of reduced complexity, this is only because of the layer by layer manufacturing. So any complexity can be manufactured. This is a NASA designed an engine fuel injector and reduced 115 individual subcomponents to 2 subcomponents. This is because of 3D printed part. The next is the time to market. With the additive manufacturing provide on demand on supply. It reduces the cost of inventory. So there's a demand, and this can be printed and directly supplied to the market. So a manufacturer, this is a manufacturer of educational laboratory equipment was able to print turbine wax mold patterns in 18 hours as a single component. In contrast to its traditional multi-printing requires 170 hours. So if had it been done by traditional methods, it could have gone up to 170 hours, which is been reduced to 18 hours only because of the 3D printing. So cost reduction, yes, I have been talking about that increased cost, but however, to some extent, some of the parts can be, some of the methods of additive manufacturing helps also in cost reduction. Like NASCAR race team adopted additive manufacturing to produce prototype parts for wind tunnel testing. Team was able to slash testing cost by 89% due to elimination of scrap and lack of tooling creation. So it also helps not only to aerospace, and this is on bionic components are also being manufactured. So Siemens has created over 10 million custom hearing aid shells using additive manufacturing and claims they provide a better fitting produce that improves customer satisfaction. This is because of the customization, the feature customization it provides. And obviously it is an eco-friendly, less material wastage. So an aircraft manufacturer reduced the mass of an engine component by 4 to 7% and generated savings up to 7,200 gigajoules of energy and 550 metric tons of CO2 equivalent emissions per aircraft annually. So when we talk about cost analysis, so there are different perspectives which we look into it. This is a management perspective, finance and accounting perspective, and manufacturing perspective. So when we talk about the management perspective, what we are referring to as the cost involved in the material and administration and capital. With finance and accounting perspective, what we are talking about the initiative, parametric, and analogical and analytical direct and overhead costs associated with the manufacturing process. With manufacturing, it's the pre-processing and the post-processing direct or indirect costs related to the manufacturing process. These all will be discussed in detail. So this is a general cost model, it has been divided into certain stages. So when we talk about the stage 1, where file and material preparation. So the process starts with the preparation of a digital file containing the necessary data on product geometry, operating parameters, and quantity. Additionally, at this stage, the raw materials are prepared. For powder materials, this can involve a sieving or a blending process. For liquid materials, this may involve a material formulation step to obtain deposable materials. Depending on the process type and machine architecture, this step may also involve the filling of raw materials and cartridges or containers, ensuring that these materials are kept under a regime that prevents degradation for a sufficient span of time. So the next step is the pre-processing. So prior to the initiation of the actual build process, the additive manufacturing machine and its control system are set up. This includes an initialization of the additive manufacturing system, energy exposure device, build atmosphere, and control computer. This is followed by setting the correct parameters in the control system. For instances, parameters for jetting based additive manufacturing include the settings for print cartridge, deposition pattern, substrate characteristics, droplet type, and jetting web form. The majority of such parameters are specific to the characteristics of the machine, material, and final products specification. So the next step involved is the build process. Since following the preparation and setup activities, the build operation is released. Most commercially available additive manufacturing technologies deposit the required build material in layer by layer fashion until the build is complete. The actual material deposition or energy delivery approach employed by the system is specific to additive manufacturing technology variants. For the investigation of additive manufacturing process economics, this is relevant since this will normally require technology specified build time estimators. Intermittent supervision of the process by technicians is also needed to monitor and control the system to minimize the risk of deviation from normal operating parameters. So the last step when the build operation is done, the as build batch of the product is removed from the machine and individual units are retrieved. This is normally done manually by human operators. For jetting based additive manufacturing process, these activities involve the removal substrate with the manufacturing objects from the machine, drying process to condition the parts for processing, and the detaching of the products from the substrate. An indispensable process element that should be included in every sessions. Additive manufacturing cost model is a product inspection step in which the manufactured objects are interrogated for fitness. From the perspective of robust cost model, the inspection step is of special interest since the point decouples the process elements that are subject to risk of failures from any subsequent activities. So when we are trying to compute the cost, like unlike the build time model developed is specified to be generic to all available additive manufacturing technologies. It includes 5 distinct cost categories like machine indirect cost, non-machine indirect cost, labor cost, material cost, and energy consumption cost. So for each process execution, the manufacturing cost is the sum of all these cost elements, such that the process cost includes the machine, non-machine, labor, material, and energy cost. To formulate the indirect cost, the machine cost rate of the IT manufacturing system, together with the cost rate of the conditioning machine, are included. The machine indirect cost is therefore dependent on both machine cost rate and usage time. The cost of materials used involves the material price and the total cost, total mass of the deposit material of final products. So here the M is represented as the mass of the material deposit. Because material losses and waste streams occur throughout the process, the material cost is modified by a waste factor, that is the omega. Hence, the material cost model can be specified as a material, which is the cost of material into mass into the omega, the waste factor. Because different systems are involved in each step, the energy consumption rates during build setup and during product conditioning vary. And thus, the overall energy consumption can be expressed by this equation: E process equal E setup into T setup plus E build into T time. The final step in this analysis is to break the cost of the process down to the unit cost level. Assuming that the products manufactured in the process are identical, unit cost thus can be expressed as C unit is a C process cost of the process by the end build time and build number of build. So now we are looking to the challenges, like the technical challenges we have discussed earlier also. Very limited materials for printing, like certain polymers, metals, and ceramics. And there's no standard for additive manufacturing process. File formats, obviously, are there. We use STL file. Process standards, quality standards. Every manufacturer has their own set. So lack of proper surface finish. Yes, we can talk about the post-processing methods which can improve the surface finish, but yet it is a area which is still is the area which needed to find it also increased production time. So with additive manufacturing, the production time is a very large. So the next challenge is the IT integration. So since every model has to be CAD model has to be printed, so CAD model is to be designed. So and with increasing in the complexity, again the CAD model has to be redesigned. However, the IT integration has revolutionized the industry for framework. And in the times of Corona, the IT manufacturing is also one of the possible solutions. With closure of international borders, STL file can be emailed and the part can be printed at the wherever there is a demand. So this can be one of the IT manufacturing can be a very good solution in recent times. And so the next challenge involves the design challenge. So we just now we have talked about the topology optimization and the design challenge, which all we required while manufacturing a part. So design and engineers have to consider like the minimum wall thickness, and this are done with the softwares. And this design challenge also is related to the IT integration, where we need softwares to optimize the designs. So the next challenge is the capability. A successful transition of IT manufacturing will require new engineering and management skills to exploit the full benefits of this technology. Although we are currently facing a significant skill gap, so we required a skillful operator for additive manufacturing. Additive manufacturing is not a technology for specialist technicians like welding, for example, but rather a field for generalists able to combine such different disciplines as mechanical, fluid, and material engineering. The next challenge is the financial challenge. Yes, we have talked about the cost models, how it is affecting the process. Like industries have always tried to reduce the cost without sacrificing with the quality of the product. So for what is the development in the near future for aerospace applications? The multifunctional structures. What it means is the enhanced design freedom and innovation shapes, weight, and material. So by this, what we mean the lightweight structure is ceramics that will enable performance at elevated temperature, can be used as bioelectric devices. with the use of functionally great materials, tailoring of mechanical and thermal responses of the components and evolution of material complexities can be done. On-demand manufacturing, yes, additive manufacturing brings this feature of on-demand manufacturing that will reduce cost and possibility of the damage during storage, and it also reduce the inventory cost. Also, it will reduce the lead time. Automated repair process will reduce cost of high value components during their lifetime. So in future, the desktop manufacturing can be possible because of the additive manufacturing. Research at the intersection of products, process, and machines. So this requires that how products, process, and machines can be correlated. Fragmentation of research investments and trends towards printing all paradigm. Like we have been talking about the printing full assemblies and joints. So every part, everything can be printed. So this can be the new trend for IT manufacturing. The need for rethinking and reorganizing the manufacturing, so the new designs can be implemented by use of the additive manufacturing. So with this, I would like to conclude. Additive manufacturing will gain more popularity and importance in upcoming years. Designers can use software to simplify geometry and reduce material and cost. Additive manufacturing provides a solution to reduce cost with design complexity. The post-processing, mechanical, and structural properties for different additive manufacturing products is an essential field of study of our future work. The possibility of using new materials in additive manufacturing is always open. However, the material is limited, but new materials can always be looked upon. To realize the full potential of additive manufacturing in the aerospace industry, a significant amount of work needs to be done for robust application. So, thank you. I am all done my presentation.
Thank you, Prasijit. It's a nice presentation, of course, definitely. But of course, I would just like to bring out our situation, ISRO, in this scenario. We have a peculiar situation, we cannot be addressed so easily by anyone, I don't think so. Because two things. One is our numbers are very less.
Okay.
Our numbers are very less, and we got established processes, which is works out to be much more cheaper than whatever we talk about now. Okay. We had a survey of migrating into 3D printing long back, 2-3 attempts we made, but whoever quoted was much more than that. There's no advantage of cost for us because of the numbers are not there. Second thing, with a lot of effort, we have indigenized, we have got multiple alloys, not single alloy. We got a lot of multiple alloys for optimization of payload and weight and the strength and your specific strength. Each product has got its own functional requirement. Functionally, the materials are a variety of materials we are using for different purposes. So the alloys, whatever we have indigenized with a lot of effort and cost and time. Now, if you want to again go back to powder for each one of these alloys, it's going to cost you much more.
Yes, sir.
We at this juncture with the study, we do not find any advantage for us for going into 3D printing. So right now we have stalled it unless just we are making it and comparing and seeing for technology purpose and technical comparison. Otherwise, no, we don't have much cost advantage right now. Okay.
No, this additive manufacturing has to be seen in totality rather than it as a replacement for the existing process of manufacturing. We have to design for additive manufacturing. Only then it becomes effective. I have one doubt actually. You said about surface finish.
Yes.
It is not up to the mark as we machine. But then what about the strength? Because it is made up of powder first.
Yes, sir. So
strength will be?
Strength will be good, sir. Strength, what we do
is good if you do hipping.
Yes, sir. Hot isolated press if you do, sir.
Hipping strength is good.
Yes, sir.
Hot isostatic process you do.
Yes, sir. Yes, sir.
Okay.
Then only the thing will be good.
Okay. Thank you. I think we have to stop.
If there are no other questions, thank you so much. At least bringing in one manufacturing paper into this because it's my domain, of course, definitely. So happy. And if you look back, I think just one sentence, we had variety, including systems, including cognitive factors of human factors, so many things, including your other things also. even applications like very futuristic applications like Panstol. All this particular last session with four were all the four purposes are different in nature. That is the thing which I found actually different in subject and different in theme, different in approach. Okay, and you have brought out something which is totally totally different, which people are not looked into, and the beautiful factors are not. But only thing for aircraft, not maybe this is going to be a good system. But of course, the particular scenario, as I just explained, was ISRO. It may be difficult for us from cost-effective point of view. It may be difficult for us to migrate to this so easily. We have to find a solution for that at least. At least for new vehicles, we can at least integrated design we can do, and joining and by riveting or welding and all we can avoid. That is one area where we can gain a lot of money and effort. And if that can offset some kind of an investment, what you're going to make for powders and other things, our jet facility and all, for powder, all these things if you're making, I think we have to study that and see, at least somewhere we have to venture into this, otherwise no, we'll be a backseat going, we had a lot of distance to cover after some time if you really want to migrate to this area. So at least for keeping us in this fray, we need to pursue this, and we have to make components, whether it is cost effective or not, because after sometimes this will be a disruptive technology, and many of the other technologies will vanish also.
Yes.
Thank you.
There was a person that had gone that raised his hand, Dr. Srihari.
Yeah, please.
I believe you had raised a hand.
Yes, am I audible, sir?
Yeah, please. Yeah.
Respected dignitaries, myself, Dr. V.M. Srihari from Associate Professor in Aerospace Engineering, Shastra University. I just wanted to thank all the respected dignitaries for this organizing this wonderful session and wonderful annual symposium. I would not be able to join the validatory function, so I wanted to convey the thanks from the bottom of my heart, and it was a very interactive and nice sessions, and thanks for all the comments from the various chair in all the sessions. So once again, I thank you, ASDB, Aerospace Division, Institution of Engineers, India. Thank you very much. Thank you, sir.
Thank you. Thank you so much. Yeah. I think it's around 2:20 now. We have to come back by 3:30. Okay, all of us, and please tell others also who are not participated in this session also, and all others also. And if Sen is there, he can send a message also or mail also to everybody saying that 3:30 is a validatory function. All chairs are supposed to be in the desk with welcome and recommendation after that and Thanksgiving.
Okay, sir. Okay.
Thank you so much. Yeah, we'll join back by 3:30 sharp. Yeah.
Thank you, sir.
Thank you, sir. Sure, sir.
Please be there. Please be there and with us till the end. Okay. Thank you so much.
Sure, sir.